Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science drifts softly through the quiet corners of the night. Tonight, we're going to talk about something that's always with you, even when you're completely still. It hums beneath your feet, carries your bed, your home, every tree, every ocean wave, every heartbeat. It's the motion of the earth itself, the slow, steady spin of our world. As you listen, maybe you can sense that faint paradox, the feeling of being perfectly still while everything you know is actually in motion. You, right now, are moving through space at hundreds of meters per second, yet your mind perceives calm. That's one of the beautiful tricks of our planet's rotation. It's constant, unbroken, seamless. We don't feel it because we move with it completely. But if you could step back far enough, if you could float out into the quiet dark beyond the clouds and look down, you'd see the world slowly turning, oceans gliding, continents passing from night into day, a blue marble gently spinning through the vast, cold silence. Before we begin unravelling why this turning happens at all, tell me something. Where are you listening from tonight? Somewhere near the ocean, maybe, where tides breathe in and out under the pull of the moon. Or perhaps you're far inland, where the air feels still and the stars seem to drift lazily across the night sky. Wherever you are, every single one of those stars seems to rise and set because the earth beneath you is rotating. The sky appears to turn, but really it's you, your city, your country, the entire planet that's spinning eastward, carrying you smoothly along. If you find this journey soothing, if it gives you a sense of peace to learn about the world in these quiet hours, I'd be so grateful if you gave the video a like, maybe even subscribed. It helps this little space of calm reach others who might also want to drift off while learning something real, something gentle. Now settle in, maybe lie back, let your breath slow a little. Because what we're about to explore is not just a question about physics. It's a question about origins, balance, and why motion itself seems to be one of the universe's favourite habits. The Earth spins once every 24 hours, completing a full rotation relative to the Sun. That spin gives us sunrise and sunset, the rhythm of light and shadow that all of life depends on. But why is it spinning at all? Why didn't our world simply form still, unmoving, hanging in space like a frozen sphere? The short answer is that motion is the rule, not the exception. Stillness in space is almost impossible. Everything that exists out there, planets, stars, asteroids, even clouds of gas, tends to rotate. And the reason comes down to something deceptively simple. When things form in space, they inherit motion from what came before. Long before Earth existed, long before there were oceans or air or even a solid surface, there was just a cloud, a vast, thin cloud of gas and dust floating in the young solar system. That cloud wasn't perfectly still. Gravity was pulling it inward, and as it began to collapse, any tiny bit of uneven motion it had started to speed up. It's the same principle you see when an ice skater pulls their arms in and begins to spin faster. In physics, it's called the conservation of angular momentum. Once something starts rotating, it tends to keep rotating unless something slows it down. So when that cloud condensed to form the Sun and the planets, each fragment of it kept a little of that original spin. The Earth inherited its rotation from that cosmic birth dance. The fascinating thing is that we can trace this story almost mathematically. Every rock, every drop of water, every molecule of air on this planet carries a bit of that ancient angular momentum. You are literally part of that spin. The atoms in your body move with the Earth, turning smoothly eastward, completing one rotation every day. At the equator, that means moving at over 1,600 kilometers per hour relative to Earth's axis. At the poles, it's slower. The motion compresses into a gentle pivot. Yet everywhere on the planet, the ground beneath us is moving in that same steady rhythm. It's strange to realise that if you were standing on the surface of the Earth watching the stars at night, What you perceive as their motion across the sky is actually your own planet spinning. For thousands of years, people believed it was the heavens that revolved around us. The constellations seemed to sweep in grand circles, the sun appeared to rise and set, and the moon glided predictably through the night. It felt natural to imagine Earth as the still centre. Only later, when astronomers began measuring, predicting and testing, did we understand that the simplest explanation was the reverse, that it's not the stars moving, but us. Even now, knowing this doesn't make it easy to feel. The spin of the Earth is constant and smooth. There's no jolt, no acceleration that we can detect. The atmosphere turns with us, the oceans move with us, and gravity holds everything to the surface. It's the same principle you experience in an airplane flying at cruising altitude. You can walk, pour a drink, even fall asleep, because everything inside moves at the same speed. Without sudden changes in motion, there's no sense of movement at all. That's why we can live our entire lives in motion and never notice. Still, the spin of the Earth affects more than day and night. It shapes weather, ocean currents, and even the pattern of life itself. The rotation causes the Coriolis effect, a subtle twisting that makes hurricanes spiral, that steers winds across continents and helps shape climate zones. It's as if the planet's spin is woven into the way air and water behave. Every breeze you feel, every wave that curls along a shore, is influenced by this vast turning beneath your feet. If you were to look from space, you'd see a perfect balance of movement. The Earth rotates eastward, the Moon orbits around us, and together we travel around the Sun, which itself moves through the galaxy. Motion nested inside motion. There's a quiet elegance to that, a reminder that everything we call normal, sunrise, sunset, the cycle of days, exists because of this rotation. Without it, half the planet would be locked in constant light, the other half in endless darkness. The balance between them would vanish. Our world would be unrecognizable, but that's the larger picture. Let's go smaller for a moment. Imagine holding a spinning top. When you first set it spinning, it's stable, balanced on its point. That stability comes from the same principle that keeps the Earth steady. A spinning object resists changes in its orientation. The faster it spins, the more stable it becomes. This is why the Earth's axis, an invisible line running from the North Pole to the South Pole, stays tilted in the same direction year after year, century after century. That tilt gives us seasons. Tilt. As the planet orbits the Sun, the northern and southern hemispheres take turns leaning toward the light, creating the familiar pattern of winter and summer. The remarkable part is that this balance has been maintained for billions of years. The Earth has been spinning since the moment it formed, and while the exact speed has changed, days were shorter long ago, about 6 hours when the planet was new, the rotation itself has never stopped. It's been gradually slowing down, ever so slightly, mostly because of the gravitational tug of the Moon. But even that process is incredibly slow. 100 million years from now, a day will be just a bit longer, barely enough to notice. Yet it means the Earth's spin is not eternal. It's a story still unfolding. That story connects us directly to cosmic history. The motion you experience every morning as the sun rises is the same motion that began over 4 billion years ago, when the early solar system was just dust and gas swirling under gravity's pull. The atoms that make up your body were once part of that same spinning cloud. You are, in a very literal sense, part of the planet's rotation, a participant in its endless turning. Even so, it's curious how easily we forget that motion. To most of us, Earth feels fixed, stable, solid. You wake, you walk, you work, you rest. The ground beneath you doesn't tremble with speed. Yet the proof of rotation is everywhere. The bulging of the Earth at the equator caused by centrifugal force. The way a pendulum swings slowly shifts direction over hours, a phenomenon first demonstrated by Foucault in the 19th century. The way satellites must account for the planet's rotation to stay in proper orbit. These aren't just theoretical curiosities. They are physical evidence that the Earth is in motion right now. If you could stand at the North Pole, you would see the stars moving in perfect circles around a single bright point, Polaris, the North Star. If you stood at the equator, you would see them rising straight up and setting straight down. Everywhere on Earth, the sky's apparent motion reflects our rotation. And if you could stop that rotation, even for an instant, the world would change in ways beyond imagination. But that's a thought we'll explore another time. For now, it's enough to recognize that the gentle turning of the Earth is one of the most fundamental, most reliable motions in all of nature. It's been the background rhythm for every life that has ever existed here. You can almost imagine the Earth as a vast clockwork sphere, silently turning in the darkness, each rotation a single tick in the long chronology of the cosmos. But unlike a mechanical clock, this one doesn't need winding. It continues because of momentum, because of the deep conservation laws that govern the universe. Energy doesn't vanish. Motion doesn't simply stop. Unless acted upon by another force, it continues. That's Newton's first law of motion, and it applies as much to planets as to pebbles. The question of why the Earth spins, then, is really a question of inheritance. We spin because the matter that formed us was spinning, because gravity, in drawing everything together, amplified that motion instead of erasing it. Because nothing in space is perfectly symmetrical, and every imbalance gives rise to movement. The laws of physics have been whispering the same truth since the first star ignited. Once something starts to spin, it keeps spinning. Our planet is no exception. As you think about that, maybe glance at a clock, or out a window if it's night where you are. The stars, the moon, even the lights of distant cities, they're all moving with you. You're part of a planet turning gracefully through space, your body and mind carried effortlessly by the same motion that governs oceans and winds. There's a kind of comfort in that. You don't need to do anything to keep it going. The Earth turns, and it will keep turning quietly, steadily for millions of years more. So, as the world continues its endless rotation beneath you, we can start to wonder about what that motion feels like. Why, even though we're moving faster than any plane or train, we experience such perfect stillness. How does that work? Why don't we feel the spin at all? The surface beneath you feels so solid, so dependable, that it's easy to forget it's in constant motion. Every mountain, forest and grain of sand, all moving together as one colossal body. Yet you can sit completely still, feel no wind of motion, no pull, no rush, and believe the world is at rest. The Earth turns quietly, invisibly, at a speed that would tear through air and water if we weren't all moving with it. It's one of those subtle truths that lives in the background of everything. The motion is there, but you and everything around you are part of the same moving system, so you never feel it. It's similar to being on a perfectly smooth train gliding across the tracks at a steady pace. When it doesn't accelerate or slow down, there's no sign you're moving. You can pour a drink, close your eyes, and feel utterly still, even though the landscape outside is sweeping past at remarkable speed. That's what the Earth's rotation is like, a smooth, constant motion, uninterrupted for billions of years. It never lurches, never stops, never speeds up in a way you could sense. The air, the oceans, and the crust itself all share that same movement, carried effortlessly along by inertia. If you stand at the equator, you're travelling eastward at roughly 1,670 kilometers per hour. That's faster than the speed of sound. Yet, there's no wind whipping past your ears, no tug on your body, no sense that you're racing through space. The reason is that everything around you, the air, the trees, your chair, even the molecules in your blood, is also moving at that same speed. You and your environment share the same reference frame, and from within that frame, everything feels still. The forces that would otherwise reveal the motion simply aren't there. because there's no change in speed or direction for you to detect. The planet's spin is steady, unbroken, smooth enough to create the illusion of stillness. If you could somehow look beyond your immediate surroundings, though, the signs of motion would become obvious. The rising and setting of the sun, for instance, is one of them. The sun doesn't truly rise or set. It's our rotation that creates that movement. Every minute the horizon beneath it shifts slightly, drawing the sun's position upward in the morning and pulling it downward in the evening. The same goes for the stars at night. They appear to drift slowly across the sky, completing a perfect circle in 24 hours. It's such a familiar sight that it hardly feels like motion at all, but that apparent movement is simply the Earth turning under the stars. What's truly fascinating is how long it took humanity to realise this. For most of recorded history, the idea that the Earth moved seemed absurd. People could feel the wind, but not the planet's motion. They could see the sun travel across the sky but had no sense of their own movement. If the Earth were really spinning, they reasoned, wouldn't we be thrown off into space? Wouldn't the air be ripped away? Wouldn't birds and clouds be left behind? Without the tools to measure such vast, smooth motion, it made sense to assume the ground was still and the heavens turned around it. Only when careful observations began to align with new mathematics did the truth emerge. Stillness was an illusion. That illusion, though, is a powerful one. Our brains are designed to detect changes, accelerations, impacts, vibrations, but not steady motion. It's part of what keeps us balanced and oriented. The fluid-filled canals inside your inner ear respond when you move or tilt your head, but if motion is perfectly uniform, they stay calm. That's why astronauts in orbit feel weightless and motionless, even though they're circling Earth at over 27,000 kilometers per hour. Constant motion without interruption feels like nothing at all. It's only when something changes, when a rocket fires, when a car brakes, that our senses react. Gravity plays its part in masking the Earth's rotation too. The force that keeps you on the ground is far stronger than the centrifugal effect of the spin. At the equator, that outward force slightly counteracts gravity, but only by a fraction of a percent. You weigh about 0.3% less there than at the poles. It's such a small difference that it would take a sensitive scale to detect it. For all practical purposes, gravity wins completely. The result is stability, the sensation of being firmly anchored to the Earth even as it races through space. There are moments, however, when the rotation does reveal itself in subtle ways. Foucault's pendulum is one example. When the French physicist Léon Foucault demonstrated it in 1851, it was one of the first simple proofs that Earth was spinning. He suspended a massive pendulum from a long wire and let it swing freely. As the hours passed, the direction of its swing seemed to rotate, but it wasn't the pendulum that was turning, it was the floor beneath it. Depending on where you are on the planet, that rotation happens at different rates. At the poles, it completes a full turn in 24 hours. At the equator, it doesn't turn at all. That slow shift is the quiet signature of the Earth's spin. If you ever visit a science museum and see one of those pendulums knocking over little pegs as the day goes on, you're witnessing the same phenomenon. It's not dramatic, but it's steady, relentless, and perfectly predictable, like the spin itself. In a way, it's humbling. The floor that feels so permanent beneath your feet is in constant motion, tracing out an invisible circle that you'll complete every day of your life. Sometimes the spin reveals itself through the sky. Near the poles, you can see the stars forming concentric circles around a single point, the celestial pole. Long exposure photographs make this motion visible, turning the night sky into spirals of light. Each streak is a record of rotation, each circle a reminder that we're turning together beneath them. It's one of those moments where the scale of motion becomes clear not through feeling, but through observation. The universe has been leaving us clues for as long as we've been looking up. The spin affects how air moves too. Because the planet is turning, winds are deflected from what would otherwise be straight paths. This deflection is called the Coriolis effect, It's why storms twist clockwise in the southern hemisphere and counterclockwise in the northern one. Air moving from the equator toward the poles doesn't travel in a direct line. It curves, following the underlying rotation of the planet. That same effect helps create the jet streams high above us, fast rivers of air that shape weather systems across the world. So, even if we don't feel the spin, we see its fingerprints in every breeze and every cloud pattern. The oceans feel it as well. Currents curve and spiral because of the same Coriolis force, creating vast gyres that circulate water across entire basins. These currents distribute heat, mix nutrients, and maintain the balance of climate. Without the rotation, global weather and temperature would be radically different. The spin doesn't just define our days, it defines the planet's living conditions. In that sense, it's not just motion, it's life's background mechanism. But there's another, quieter reason why we don't feel the Earth turning. Our bodies are deeply adapted to it. Every organism on Earth evolved under the same rotation rate. Our internal clocks, our circadian rhythms, are tuned to a roughly 24-hour cycle, because that's how long it takes the planet to turn once. The rising and setting of the sun, the ebb and flow of light, became part of our biology long before we understood what caused it. In a way, you could say that the spin of the Earth isn't just something happening outside us, it's written into our systems. Every cell in your body follows that rhythm. Even the small mechanical details of the spin are fascinating. The Earth isn't a perfect sphere, it's slightly flattened at the poles and bulges at the equator. That shape exists because of rotation. The centrifugal force pushes outward just enough to widen the equator. Without that, the planet would be nearly spherical, but as it is, it's more like a gentle oblate spheroid. This shape, though subtle, affects gravity, ocean levels, and even how satellites orbit. The tiniest variations in the spin create measurable effects in navigation, timekeeping, and spaceflight. And yet, for all that measurable impact, we still experience serenity. That's the paradox that makes this subject so comforting. You're moving faster than you can imagine, yet everything feels peaceful. There's something grounding about that. A reminder that motion doesn't always mean chaos. Sometimes motion means balance. The quiet whirl beneath your feet isn't there to disturb you. It's there to hold everything together. A motion so consistent that life could build entire ecosystems upon it without even noticing. It's also a reminder of how relative motion really is. From your point of view, sitting quietly, it's the stars that move. From an astronaut's point of view above the planet, it's you who turns. Both views are correct in their own way. Physics doesn't require a single, true motion, only relationships between moving things. So, while we say the Earth spins, we could just as easily say the universe turns around us, depending on where we choose to measure from. It's a simple truth that the feeling of motion depends on your frame of reference. That idea, frames of reference, is at the heart of why we experience such calm on a spinning world. Everything in your immediate frame moves together. You, your house, the trees, the atmosphere, all share the same rotational velocity. You don't notice the motion because nothing within that shared system is changing relative to you. If you suddenly rose high above the surface and stayed still while the planet turned beneath, then you'd see motion. But as long as you move with it, it's invisible. Our ancestors noticed this stillness long before science could explain it. Ancient observers built sundials and stone circles to track the apparent movement of the sky. They saw the stars rise and set, they watched shadows shift through the day, and they found comfort in the reliability of it all. Even without knowing that the Earth was turning, they built entire calendars and rituals around the pattern. In that sense, the stillness we feel isn't ignorance. It's part of the experience of being alive on a stable, spinning world. If you could freeze time and somehow make the Earth transparent, you'd see a complex ballet beneath the surface. Molten rock slowly churning in the mantle, tectonic plates gliding at the top, ocean currents flowing, air moving, clouds forming, all of it happening while the whole planet spins. The motion we can't feel is layered with motions we can barely comprehend. Yet the effect, when you zoom out, is a single, unified rotation. A planet quietly turning in the dark, balanced between forces that have been in play since the solar system's beginning. Sometimes, when scientists measure the planet's rotation with extreme precision, they find tiny variations, milliseconds added or subtracted from a day. These changes come from shifts in mass distribution, melting ice, earthquakes, ocean currents, even strong winds. When air moves across the surface, it slightly alters how the Earth spins, much like a figure skater adjusting their arms. The changes are tiny, but measurable. It's astonishing that something as vast as the Earth can respond to something as fleeting as weather. But it does. The planet's spin is stable, but never static. It's alive in its own quiet way. All of this movement, though invisible, forms the foundation of everything familiar. The 24-hour rhythm sets our clocks, our habits, and even our sense of time itself. Every sunrise, every shadow, every tide depends on it. You don't have to think about it or maintain it. It's just there, humming gently beneath your existence. You could almost call it the background heartbeat of the planet, steady, ancient, and unbroken. If you were to imagine it physically, the motion of the Earth beneath your bed, beneath the streets, beneath the oceans, you might picture a vast globe spinning silently in blackness. No sound, no vibration, just a constant turn. It's hard to reconcile that image with the feeling of stability we have on the surface. But that's what makes it so extraordinary. We live on a moving world that feels perfectly still. It's as though nature found the perfect equilibrium between motion and calm. That equilibrium defines our experience of home. The ground doesn't shake, the air doesn't rush away, and the oceans don't spill off into space. Everything stays bound by gravity and inertia, two simple forces working together to create a world that moves endlessly while remaining stable enough for life. That balance is delicate but astonishingly robust. The Earth has been turning this way for billions of years, and unless something massive interferes, it will continue for billions more. When you lie down at night and the stars seem to drift slowly past your window, that's the planet's rotation carrying you gently eastward. You're part of that motion, completely embedded in it. You're not standing still on a spinning world, you're a moving part of it, woven into its rhythm. There's something quietly reassuring in that thought, that even in rest, you're moving with the cosmos, part of a pattern that began long before you and will continue long after. The quiet whirl beneath your feet isn't something to notice, it's something to trust. It means the laws of physics are working exactly as they should. It means the world is stable, predictable, safe enough for sleep, thought, and everything in between. And as you sense that calm, maybe it's worth wondering how this motion began in the first place. What caused the Earth to spin when it first formed, and why did it never stop? Long before the blue oceans, before mountains, clouds, or even the solid crust beneath our feet existed, the Earth was not yet a planet. It was a gathering, a slow and unsteady collection of dust, ice, and gas orbiting a young, violent sun. To picture that ancient time, you have to imagine not a calm solar system like the one we live in now, but a storm, a vast, swirling disk of debris spinning around the newborn star at its centre. Everything that would one day become our planet was suspended in that haze, colliding, clumping, and falling together under gravity's endless pull. This was the beginning of motion as we know it. When gravity starts to draw matter inward, it never does so perfectly evenly. There are always small differences in density, tiny imbalances in how things move, and every imbalance means movement. In the early solar nebula, particles were drifting and colliding, sticking together through static charge and mutual gravity. The whole cloud rotated slowly around the sun, and as it shrank it began to spin faster, conserving angular momentum the same way a spinning skater does when they pull their arms in. From that immense rotation, every planet's spin was born. At first, the proto-Earth was just one of countless small objects orbiting the sun. It didn't have an atmosphere, oceans, or even a defined surface. It was more like a cluster of molten rubble, a growing embryo of rock and metal. Each time it collided with another body, sometimes as small as a mountain, sometimes as large as Mars, it changed shape and gained mass. These collisions were not gentle. They released unimaginable energy, melting rock, vaporizing metal, and reshaping the young world over and over again. Through all of it, angular momentum built up. Every glancing impact added a twist, a spin, a push that contributed to the rotation we still live within today. The scale of that chaos is almost impossible to picture from the calm surface of our modern planet. The early solar system was a crowded place. Billions of rocky fragments orbited the sun, crossing paths, crashing, merging, or breaking apart again. Gravity was the only sculptor, and its chisel was motion. Slowly, over tens of millions of years, a few large bodies began to dominate. The seeds of the planets. The one that would become Earth was about halfway between the Sun and the outer gas giants, where conditions allowed rocky material to survive. It spun faster than it does now, completing a rotation in just a few hours. In that rapid spin lay the foundation for every sunrise and sunset we know. The physics of it is beautifully simple. When a cloud of gas collapses, the total angular momentum remains constant. The particles within it move faster as they come closer together. You can see the same thing in miniature when a figure skater brings in their arms. Their rotation speeds up because their mass is now concentrated closer to their centre. The early solar nebula worked the same way. As gravity pulled it inward, it spun faster. The material within that disk then began forming smaller whirlpools, eddies of dust that clumped into protoplanets. Each one inherited part of the rotation of the larger system, but each also developed its own unique spin depending on the collisions it experienced. That's why the planets in our solar system all rotate, but at different speeds and in slightly different directions. Earth's early rotation was shaped not only by how it formed, but by what struck it afterward. One collision in particular changed everything. About 4.5 billion years ago, a Mars-sized object, now often called Theia, slammed into the young Earth. It wasn't a direct hit, more of a glancing blow. The impact released more energy than anything that has happened since, melting much of the surface and hurling vast amounts of rock into space. Some of that debris coalesced into the moon. The rest settled back onto Earth. The collision didn't just reshape our planet, it adjusted its rotation and tilt. From that moment, Earth's spin slowed slightly, and its axis tilted to about 23.5 degrees, a tilt that gives us seasons, climate patterns, and the shifting path of sunlight through the year. After the chaos began to settle, the Earth was still molten, a glowing sphere surrounded by vaporized rock and metal. The surface was an ocean of magma, constantly churning, cooling, and hardening at the edges. The rotation continued, steadying as the planet's mass evened out. Within a few million years, heavy materials like iron and nickel sank toward the center, forming the core. Lighter materials rose to the surface. That separation helped stabilize the spin. The core became a dense anchor, while the mantle and crust cooled enough to create the beginnings of solid land. Even then, the young planet was spinning far faster than it does today. A full rotation may have taken only 6 or 8 hours. That rapid turn meant fierce winds, turbulent atmosphere, and immense tidal effects from the nearby moon. The gravitational pull between Earth and Moon began a slow exchange of energy that continues to this day. The tides, both in the oceans and in the rock itself, acted like brakes, gradually transferring rotational energy from Earth to the Moon's orbit. As a result, the Earth's day lengthened, and the Moon slowly drifted farther away. But in those early eons, everything was still finding balance. The rotation rate fluctuated slightly with each major collision, but the overall momentum remained. There was no mechanism to stop it entirely. Space has no friction in the way we experience it on Earth. Once a body starts spinning in the vacuum of space, It keeps spinning until something exerts a significant force on it. There was nothing large enough to stop the Earth's rotation completely, only small influences that changed its speed or direction. That's why, even after billions of years, our planet is still turning. As the crust solidified and the first oceans formed from condensed water vapor, the Earth began to resemble something closer to what we know. The atmosphere thickened, cooling the surface and softening the heat that had once glowed from below. The spin now set the rhythm for days and nights. Temperatures rose and fell in cycles. Light and darkness alternated with dependable precision. For the first time there was a regular pattern, a rhythm that living things could one day adapt to. That rhythm of rotation would become the metronome for life itself. If you could somehow watch that period unfold, you'd see a world glowing with volcanic fire, wrapped in dense clouds, turning endlessly beneath a dim young sun. Lightning would flash through the atmosphere, striking pools of water rich in carbon compounds. Each rotation brought cooling and warming, energy and rest, chaos and calm. The cycle was relentless, and it was essential. It set the stage for the complex chemistry that would lead to life. The planet's spin, inherited from cosmic collisions and gravity's laws, became one of the defining features of its environment. What's interesting is how stable that spin became once the major bombardment ended. The angular momentum locked in. Minor adjustments occurred through interactions with the moon and the sun's gravity, but nothing dramatic. The same rotation that began billions of years ago is the one we still experience now, only slightly slower. The idea that something so ancient could continue so flawlessly is part of what makes studying planetary motion so awe-inspiring. It's as though the Earth remembers its birth, carrying forward the motion it was given in its cosmic childhood. When scientists model this process, they use the language of physics: energy, momentum, mass distribution. But underneath those numbers is a simple truth: everything moves because it must. The universe doesn't allow stillness to last. Gravity and inertia ensure that once something starts to move, it keeps going. Planets spin because they were born in motion. That motion is conserved because nothing in the vacuum of space can truly resist it. If you could look beyond Earth to the other planets, you'd see the same principle at work. Jupiter spins in just 10 hours. Venus spins so slowly that its day is longer than its year. Uranus spins on its side. Every world carries a different story of collisions, accretion, and inherited angular momentum. Each is a record of its own chaotic formation. Earth's story just happens to be the one that produced oceans, weather, and the delicate balance that allows life. Its spin has remained fast enough to maintain a stable day-night cycle, but slow enough to allow moderate temperatures. That combination, as simple as it sounds, is vital. If the planet spun much faster, winds would be extreme, weather unpredictable, and temperature differences between day and night too small to support the same kind of life we know. If it spun much slower, days and nights would stretch into weeks or months, making half the planet too hot and the other half too cold. The current rotation rate sits right in that narrow band of balance. As Earth continued its slow evolution, that balance allowed continents to form and drift. The rotation influenced ocean currents and atmospheric circulation. It also affected how energy from the sun was distributed, helping shape climate zones. The equator received more direct sunlight, the poles less, creating the temperature gradients that drive global weather. All of that stems ultimately from the fact that the planet spins. It's remarkable how much depends on something so fundamental and constant. Even timekeeping itself, the most basic measurement of existence, is tied to that rotation. Before we had atomic clocks or GPS satellites, before civilization even had writing, people measured time by watching the sky. The length of a day was defined by how long it took the sun to return to the same position. That's the Earth's rotation. Every hour, every calendar, every rhythm of daily life is anchored to that ancient spin inherited from a collapsing cloud of gas. In that sense, every clock is really just a reflection of the planet's motion, a small imitation of a much larger and older cycle. Thinking about this long chain of cause and effect brings perspective. The rotation that keeps the world turning today began in a time before oceans, before mountains, before even the concept of day existed. It was established when the solar system was still a turbulent swirl of dust and gas. Each collision, each gravitational tug, added to the momentum until a stable pattern emerged. The Earth has never stopped turning since. The same law of motion that keeps a child's spinning top balanced keeps our entire planet in motion through space. Every so often, scientists look for traces of that early rotation locked in geological records. The way certain minerals form, the alignment of ancient magnetic fields, even the growth rings in coral can tell us how long days were hundreds of millions of years ago. Those records confirm that Earth's rotation has been gradually slowing. In the time of the dinosaurs, a day was about 23 hours long. Hundreds of millions of years before that, it was shorter still. The reason, as always, is the moon. Its gravitational pull raises tides in the oceans, and as water moves, it rubs against the sea floor, converting rotational energy into heat. The result is a minuscule but cumulative loss of spin. The Earth's day lengthens by about 1.7 milliseconds per century, almost nothing to us, but over geological time it adds up. That slow deceleration is another reminder that the planet's rotation is a dynamic process, not a fixed one. It's easy to imagine it as eternal and unchanging, but every movement has consequences. The tides we see each day, the erosion of coastlines, even the moon's increasing distance from Earth, all trace back to the way the planet spins. Motion creates interaction, and interaction creates change. The rotation is both the cause and the witness of Earth's history. In its cosmic childhood, the Earth was like any newborn, energetic, unstable, constantly changing. Its spin was fast and irregular, its surface molten and restless. Over billions of years, that wild energy settled into the calm, steady motion we experience now. Yet that stability didn't erase the past. Every turn of the planet is a continuation of that original momentum. The same physical principles that shaped the early solar system still govern our world today. Gravity still pulls, inertia still preserves, and the Earth keeps turning, just as it always has. From the perspective of deep time, that's a comforting thought. The spin of our planet isn't a temporary quirk or a fragile coincidence. It's a natural outcome of the universe's mechanics. It connects us directly to the origins of everything, to the spinning disks of stars forming in distant galaxies right now, to the same processes that shaped other worlds before ours and will shape others after. The rotation of the Earth is a thread that runs through the story of matter itself. It's part of a universal pattern. Everything moves, everything turns, everything seeks balance through motion. When you think of the Earth's spin that way, it becomes more than just a scientific fact. It's a reminder of continuity. The planet beneath you is performing the same motion it has for billions of years, the same motion it inherited at birth. It doesn't need effort or energy input. It simply continues because the laws of physics require it. From the chaos of its cosmic childhood came a steady rhythm that defines our existence, a rotation that brings morning, night, weather and time itself. And as you lie there now, somewhere on the surface of that same world, carried smoothly through space by its unending spin, you're connected to that origin story. Every second of your day, every night's sleep, is part of the same rotation that began when the solar system was young. The quiet world beneath your feet isn't just motion, it's memory, preserved in movement, continuing without pause. The planet kept changing long after it found its spin. The collisions quieted, the surface cooled, and life began to emerge under the steady rhythm of rotating days. The Earth never decided to spin, and it never chose to keep going. It simply hasn't found a reason to stop. Out there in space, motion continues until something interferes with it. Friction, drag, resistance. Those are things that belong to air, water, and surfaces. In the vacuum of space, there is almost nothing to slow a planet down. So, once the Earth began turning in its early years, that rotation became a kind of permanent inheritance, an unbroken motion passed forward through every second since. You can think of it as the ultimate momentum, a motion so vast, so smooth, that it's continued for billions of years without any engine, any push, any fuel. Just the quiet persistence of physics. The law that explains this is one of the simplest and most important in all of science, Newton's first law of motion. It tells us that an object will keep moving at a constant speed in a straight line, or rotating at a constant rate, unless a force acts upon it. That's the principle of inertia. It sounds ordinary, but in the context of the entire planet, it's profound. Once the early Earth started spinning, nothing in the vacuum of space was strong enough to stop it. Gravity keeps the planet's shape, but gravity doesn't resist rotation. It doesn't cause friction. It just holds everything together while the spin continues, silently, ceaselessly. It helps to imagine what space actually is. Not emptiness exactly, but close. There's no air to push against the surface of the planet, no fluid to create drag. When you push something across a table, it stops because friction transfers the energy into heat. When a planet spins in the vacuum of space, there's nothing to take that energy away, so it keeps turning. And because it's massive, nearly 6 sextillion tons, its momentum is enormous. That momentum is what makes the spin so stable. To slow it meaningfully, you would need an incredible force, something powerful enough to alter the planet's entire distribution of mass. Nothing like that has happened since the early collisions that formed the Moon. Even the pull of the Moon and the Sun, though constant and measurable, can only make small adjustments over enormous stretches of time. Those tidal forces have been gradually slowing the Earth for billions of years, but so gradually that you'd never notice. The length of a day has increased by a few hours since life first began, and it continues to grow by about a couple of milliseconds every century. That's the tiny cost of the energy the tides steal from our rotation. Some of that energy lifts the Moon slightly higher into its orbit. The rest is lost as heat in the oceans. But the spin itself, the fundamental rotation, continues. There's a kind of beauty in how that works. You don't need a motor to keep the planet turning. You don't need a constant input of energy. It's a self-sustaining motion, powered by nothing, opposed by almost nothing. It's motion in its purest form, where energy isn't lost, just preserved in the steady turning of a world. The only things that can slow it are those tiny interactions with gravity and tides, and even they can't stop it entirely. They can only stretch the rhythm over vast spans of time. If you were to watch Earth from far away, say, from a point near the Moon, you'd see it turning with perfect consistency. Every 24 hours, the same continents roll back into view. The atmosphere moves with it, swirling and shifting, but the bulk of the planet turns in a smooth, stable rotation. From that vantage point, it would look timeless. You'd see the same movement that's been happening since long before life began, the same spin that guided the first shadows across stone and water, the same rotation that makes a day what it is. The planet doesn't speed up, doesn't stutter, doesn't slow in any way that your eyes could detect. It's a silent, eternal revolution. It's difficult to grasp what it means for something to have been spinning non-stop for billions of years. Even the idea of a billion is hard for the human mind to picture, but that's how long this motion has lasted. Every sunrise you've ever seen is a continuation of that same movement. Every orbit of the Moon, every wave, every rotation of a compass needle, all of them are tied to that same ancient spin. It's not just part of Earth's character, it's part of what defines it as a planet. In fact, rotation is one of the key features that separates a planet from a dead piece of drifting rock. Spin creates flattening at the poles, bulging at the equator. It shapes magnetic fields. It stabilizes orbits. It gives a world a kind of personality, a rhythm. The magnetic field in particular is a fascinating product of this motion. Deep inside the Earth, the outer core is made of molten iron and nickel. That metal flows and circulates, driven by heat escaping from the planet's interior. Because iron is conductive, and because the whole planet is spinning, those moving fluids generate a magnetic field through what physicists call the dynamo effect. The rotation helps organize those flows into large-scale currents, which in turn sustain the field that surrounds the Earth. Without that rotation, the magnetic field would collapse, and with it, our protection from the solar wind. The atmosphere would be slowly stripped away, as it was on Mars. So the spin doesn't just keep the planet moving, it keeps it alive. The steadiness of Earth's rotation is another thing worth noticing. Most objects that spin in space eventually wobble or tilt. They don't stay perfectly aligned forever. The Earth does wobble slightly, a movement called precession, caused by the gravitational tugs of the Sun and Moon on its equatorial bulge. But that motion is slow, so slow it takes about 26,000 years to complete a single cycle. That means the North Star changes over time, but the overall tilt stays stable enough to preserve the seasons. Even the small irregularities in the spin, caused by earthquakes or changes in ocean mass, are minuscule compared to the planet's overall motion. The result is a world that has been turning with remarkable smoothness for most of its existence. To see just how persistent that motion is, you can look at other spinning bodies in the solar system. Jupiter, for example, is the fastest spinner. It completes one rotation in just under 10 hours. Its enormous size and gaseous nature mean its equator bulges dramatically. Yet it too has been turning since it formed. Mercury, by contrast, spins very slowly. Its day lasts nearly 2 Earth months. But even that sluggish motion has continued unbroken. Venus rotates backwards compared to most planets, likely due to a violent collision in its past. Mars spins at almost the same rate as Earth, giving it similar day lengths. Everywhere we look, the story is the same. Once a planet starts spinning, it never really stops. What's particularly intriguing about Earth's rotation is how it interacts with everything else. Because it turns eastward, the sun appears to rise in the east and set in the west. That simple effect shapes our entire perception of time. Every culture, every calendar, every moment of daily rhythm depends on that steady rotation. The planet's spin is the basis for hours, days, and years. Without it, time as we understand it would feel meaningless. Our bodies, our routines, even our language are tied to that constant turning. The constancy also affects how our atmosphere behaves. The Coriolis effect, the deflection caused by the spin, gives shape to global wind patterns. Air flowing from the equator toward the poles curves to the right in the northern hemisphere and to the left in the southern. That curvature creates trade winds, jet streams, and the great circulating cells that distribute heat and moisture around the world. Without the Earth's rotation, weather would be radically different, simpler perhaps, but far less balanced. The spin introduces complexity, and in that complexity life finds its niches. Ocean currents respond in much the same way. The rotation helps form the great gyres, enormous loops of water that move heat around the planet. The Gulf Stream, for instance, carries warm water from the tropics toward Europe, moderating its climate. The spin of the planet is part of what keeps that current stable. These movements of air and water are like the heartbeat of the world, driven in part by the steady turning beneath them. When you think about it, every breeze that brushes your skin, every wave that curls and breaks, is connected in some small way to that unending spin. It's strange to think that something as intangible as motion could have such tangible effects. The Earth's rotation doesn't make noise, you can't see it directly, but it defines nearly everything about how the planet behaves. Even gravity is subtly shaped by it. At the equator, the centrifugal effect from rotation slightly counteracts the pull of gravity. making you weigh a fraction less than you would at the poles. The planet itself bulges outward there by about 43 kilometers, giving Earth its slightly flattened shape. None of that would exist if the planet weren't spinning. If somehow, through some impossible intervention, the Earth was stopped, the consequences would be catastrophic. The momentum of the oceans and atmosphere would continue, sweeping across the surface with unimaginable force. Mountains would crumble, seas would surge, and the planet's balance would collapse. Fortunately, there's no realistic way that could happen. The amount of energy required to halt the planet's rotation is beyond comprehension. Even the combined gravitational forces of the Sun and Moon can only slow it by fractions of a second over millions of years. The Earth's spin is as close to eternal as anything physical can be. In the long run, though, it will change. The same tidal interactions that lengthen our days will continue to do so until, far in the future, Earth and Moon become tidally locked, each showing the same face to the other, just as the Moon does to us now. When that happens, a day on Earth will last as long as a lunar month, about 47 current days. But that's billions of years away, long after the Sun has begun to change and our planet's surface has transformed completely. For all practical purposes, the spin that began at the dawn of the solar system will last for the lifetime of the Earth. There's a kind of serenity in realizing how stable that motion is. Every generation, every life, every story is unfolded under the same rotation. The continents drift, the atmosphere shifts, species come and go, but the planet keeps turning. It's the one constant in a world defined by change. The sun will rise tomorrow not because someone winds a clock, but because the planet hasn't forgotten how to move. Even though it's mechanical at its core, there's something oddly comforting about that. The same laws that keep a stone falling to the ground are the ones that keep the Earth rotating. The universe doesn't have to think about it or maintain it. It just works. Motion persists. The equations that describe it are the same everywhere, from galaxies to atoms. They're reliable, unchanging, and universal. That reliability is what allows us to measure, predict, and understand. It's also what allows life to adapt and thrive. If you could trace a single point on the Earth's surface through time, it would describe a spiral through space. As the planet turns, it also orbits the Sun, and the Sun moves through the galaxy. The path isn't a circle, but a long, graceful helix winding outward. Every turn of the planet adds another loop to that spiral, another day in the long record of its motion. From a cosmic perspective, the Earth is like a dancer spinning while moving across a vast stage. The spin never stops, but the background keeps changing. That's why no rotation is ever identical to the one before it. The orientation, the position, the light. Something is always subtly different. Even with all these movements layered together, the rotation remains the core motion we experience. It defines what we mean by day. It gives the planet its pulse. Everything else, the orbit around the Sun, the motion through the galaxy, happens on such a scale that we can't perceive it directly, but we can perceive the spin. We see it in the arc of shadows, in the cycle of dawn and dusk, in the steady rhythm of time passing. The constancy of that rotation is what gives our world structure. Without it, the concept of time would lose its anchor. The idea that motion can exist indefinitely without energy input still surprises people. It feels unnatural because in everyday life, everything slows down eventually. A spinning wheel stops, a car coasts to a halt. A pendulum loses momentum. But that's because all those things exist in environments full of friction. The molecules of air, the texture of surfaces, the tiny collisions between particles, all of them steal energy and convert it into heat. In the vacuum of space, there's none of that. The only things that can alter motion are external forces, and for the Earth those forces are weak and distant. That's why the spin has lasted for so long, and why it will last for so much longer. Even now, scientists measure tiny fluctuations in the Earth's rotation using atomic clocks and laser satellites. They can detect changes as small as microseconds per day, caused by earthquakes, shifting ice caps, and movements of air and water. When massive glaciers melt, they redistribute weight across the planet, slightly altering its spin. When earthquakes shift the crust, they can speed it up or slow it down by a fraction of a millisecond. These effects are minuscule, but they show that the planet is a living, dynamic system, constantly balancing itself while maintaining that core motion. It's not a rigid, mechanical sphere. It's a flexible, layered world whose spin responds subtly to everything happening within and around it. The persistence of the Earth's spin has another implication that touches everything alive. It's the basis of biological rhythm. Every organism on this planet, from bacteria to humans, carries an internal clock that aligns roughly with the 24-hour cycle. This circadian rhythm regulates sleep, feeding, hormone release, and countless other processes. That connection between biology and planetary motion is ancient. It evolved because the planet's rotation was so dependable that life could use it as a framework. The cells of your body know when to rest and when to wake, because they've inherited that rhythm from millions of generations before you, all living under the same turning sky. When you step back and think about it, the spin that never stopped is one of the quietest yet most powerful forces shaping existence here. It dictates the length of a day, the pattern of climate, the orientation of magnetic fields, and the rhythm of life. And it does all this without sound or effort. Its motion distilled to its purest form, endless, steady, indifferent, and yet profoundly sustaining. You could live your entire life and never feel it, but it's always there, beneath your feet, beneath every breeze, beneath the beating of your own heart. It's the reason dawn arrives at a predictable hour and stars wheel gently across the sky. It's the reason compasses work and tides rise. The spin is not something that happens to the Earth. It is the Earth. It's what makes our planet a living participant in the cosmic dance, rather than a silent drifting stone. And that motion, as constant as it seems, carries with it traces of the past, of collisions, gravity, and time itself. It connects us to the birth of the solar system and the distant galaxies that spin for the same reason. When you realize that, you begin to see that the Earth's rotation isn't an isolated phenomenon. It's part of a pattern that repeats across the universe. Everything spins because everything was born from motion. Nothing ever truly begins at rest, and nothing ever truly stays still. If you could look back in time to the earliest days of the solar system, you wouldn't recognize anything familiar. There would be no calm blue sky, no oceans, no land masses, no clouds or seasons. There would be only fire, dust, and collision. The young Earth was one of countless bodies forming from the debris of a collapsing nebula, and in that crowded, restless environment, nothing moved in perfect harmony. Each orbit crossed another. Each young planetesimal tugged and bumped against its neighbours, and every impact changed something. The shape, the temperature, the rotation. The story of why the Earth spins the way it does can't be told without these collisions. They were the sculptors of everything stable we know now. In those first few tens of millions of years, the solar system was violent. Gravity had drawn the material together, but it hadn't yet smoothed the orbits or separated the planets into the neat arrangement we see today. Instead, it was a cosmic construction site, fragments of rock and metal hurtling around the sun, crashing together, breaking apart and merging again. Every impact added momentum or stole it. Some slowed rotation, others sped it up. The result was chaos slowly moving toward order, and the Earth's steady spin is one of the few survivors of that ancient turbulence. Each collision left behind energy that had to go somewhere. The kinetic energy of one body meeting another at thousands of kilometers per second didn't just vanish. It became heat. The surface of the young Earth melted again and again, creating vast oceans of magma that boiled and churned under a dense, toxic atmosphere. Gravity held everything together, but the shape, the tilt, and the speed of the rotation were all being rewritten each time a new object struck. Over and over, these collisions adjusted the world's balance like a sculptor reshaping clay. And the masterpiece that eventually emerged, a planet with a 23.5-degree tilt, a 24-hour day, and a single large moon, is the product of that cosmic craftsmanship through violence. One of those impacts was unlike any other. It was enormous, catastrophic, and decisive. A body roughly the size of Mars, known to scientists as Theia, crossed Earth's orbit around 4.5 billion years ago. Its trajectory was slightly off-center, so instead of a head-on crash that would have destroyed both worlds, it delivered a glancing blow. But even a glancing blow at cosmic scale is enough to remake a planet. The collision melted much of the crust and mantle, ejecting vast amounts of debris into orbit. That debris circled Earth for months, maybe years, before gradually coming together under its own gravity to form the Moon. That event, sometimes called the Giant Impact, changed everything. Before it, the Earth's rotation may have been faster, possibly with days lasting only 6 hours. The impact slowed it slightly, but it also gave it stability. The new moon's gravitational pull began to act as a steadying hand, damping the chaotic wobbles that came from smaller collisions and helping the planet maintain a regular tilt. The tilt itself, likely a direct result of the impact, gave us seasons. Without that angle, the sun would rise and set in the same place every day of the year, and most of the planet would have little variation in temperature or daylight. That single collision, unimaginably violent in its moment, may be the reason life later found such comfortable patterns of light and warmth to evolve within. It's strange to think of such destruction leading to balance, but that's the pattern the early solar system followed. The collisions that vaporized mountains and boiled oceans also built the long-term stability we now depend on. They redistributed angular momentum, the fundamental currency of motion in the cosmos, and that redistribution set the rotation rate that still defines our day. Once the dust settled and the crust cooled, the Earth was left spinning smoothly, tipped just enough to create climate variation, and accompanied by a moon large enough to stabilize its axis. The chaos of impact had created the calm we live in. But even after that great collision, smaller impacts continued to shape the world. Asteroids and comets struck regularly, leaving craters and adding mass. Some slowed the spin slightly by transferring their momentum in the opposite direction. Others sped it up in small increments. Each event was a reminder that the planet's rotation wasn't set in a single instant, but adjusted, refined, and stabilized over time. The record of those impacts still exists in the scars scattered across the lunar surface. The Moon, lacking atmosphere and geological renewal, keeps its history visible. Earth's surface, with its erosion, volcanoes, and moving continents, hides most of its wounds. But the memory of those collisions lives in its structure, in its tilt, and in the Moon's orbit itself. The relationship between Earth and Moon became one of the most important outcomes of that early chaos. The Moon's gravity began pulling on the bulging equator of the rotating Earth, creating tidal friction that slowly transformed both worlds. Each tug stretched the planet slightly, creating tides not just in the oceans but in the crust. The resistance of that stretching generated heat, which dissipated some rotational energy. That's why Earth's rotation gradually slowed while the Moon drifted outward. It's an ongoing echo of the ancient impact, a slow exchange of motion that continues billions of years later. What began as collision turned into a dance, and that dance governs the rhythm of days, tides, and even biological cycles. If you think about how precise this system is now, a 24-hour day, a moon that always shows the same face, predictable tides rising and falling. It's remarkable that all of it was born from chaos. There was no design in it, only physics. The outcome we experience is one of balance emerging from randomness. Each collision was like a coin toss, its energy reshaping the planet's motion, and through sheer probability and persistence, the result became a world capable of stability. The Earth's spin isn't a fragile miracle. It's the inevitable product of motion finding equilibrium in the vacuum of space. It's easy to imagine that once the big collisions ended, the planet simply cooled and settled, but even that process was full of smaller adjustments. When molten rock solidified into crust, the mass distribution changed slightly, shifting the axis by minute degrees. When the first deep oceans formed, their weight redistributed along the equator, changing how the planet's mass was balanced. These effects might seem trivial, but for a rotating body, even tiny shifts can have measurable consequences. Over millions of years, those subtle changes refined the spin further, making it smoother, more even, more predictable. Scientists studying this long history can still see traces of those adjustments. For example, Earth's moment of inertia, the way its mass is distributed relative to its rotation, affects how it spins. When glaciers form or melt, they shift that balance, slightly altering the speed of rotation. During the ice ages, as ice sheets built up over the poles, the added weight slowed the spin just a little. When they melted, the rotation sped up again. These fluctuations are minute, milliseconds per century. But they remind us that the spin is not an unchanging constant. It's a living property of a living planet, shaped continually by what happens on and within it. The early bombardment that delivered those formative collisions also brought the ingredients of life. Many scientists believe that comets and carbon-rich asteroids delivered water and organic molecules to the surface. The spin of the planet, by creating day-night cycles and weather patterns, helped distribute that material evenly across the globe. As the bombardment slowed and the surface cooled, the Earth's steady rotation became the foundation for environmental stability. Days and nights began to settle into regular lengths. The extremes of heat and cold moderated. In that predictable rhythm, chemistry had a chance to become biology. You could say that rotation and collision were partners in creation. The impacts provided the material and energy, and the spin provided the rhythm that allowed complexity to emerge. Without those collisions, there would be no moon to stabilize our tilt, no balanced cycle of seasons. Without the spin, there would be no day or night, no regular temperature variation, no climate balance. Together, they turned the violent beginnings of the planet into the conditions for life. That's one of the deeper paradoxes in Earth's story. The gentle regularity of our days depends on ancient chaos. It's easy to forget how precarious that early balance was. A slightly different impact could have tilted the Earth far more, producing extreme seasons or even making it roll on its side like Uranus. A different speed of rotation could have changed the length of the day, altering everything from climate patterns to atmospheric stability. But the collisions that actually happened left us with a near-perfect equilibrium. A tilt that gives warmth to one hemisphere while cooling the other. A rotation that creates livable cycles of light and darkness. The planet found a sweet spot in motion, not because it was designed to, but because physics allows balance to emerge from disorder when given enough time. The scars of those cosmic bumps can still be seen if you look for them. Impact craters dot the continents, though most have been eroded or buried by geological processes. Beneath the oceans, hidden under layers of sediment, there are ancient basins formed by impacts so large they affected the entire planet's climate. One of the most famous, the Chicxulub crater in Mexico, marks the event that ended the age of the dinosaurs 66 million years ago. That collision didn't change the planet's rotation in any meaningful way. It was far too small for that, but it shows that the era of impacts never truly ended. The scale just diminished. What once were world-making collisions became extinction-level events, and eventually smaller meteor strikes that barely leave a mark. If we could see all of them together, mapped over time, it would look like a long record of adjustment. Each impact a note in the planet's ongoing song of motion. The biggest ones altered its rhythm permanently. The smaller ones left echoes that faded quickly. But none of them ever stopped the spin. They couldn't. The energy of rotation, once established, is too immense to be undone except by forces of unimaginable scale. The collisions of Earth's youth were powerful enough to shape that motion, but now only gradual internal processes or external gravitational interactions can continue to fine-tune it. What those impacts did leave us, though, is the moon. and the moon has been Earth's silent companion in maintaining that spin ever since. Its gravitational influence not only controls the tides, but stabilizes the planet's axial tilt. Without it, the tilt would drift chaotically over millions of years, leading to erratic and extreme changes in climate. Mars, which lacks a large moon, shows evidence of just such instability. Its tilt can vary dramatically, sometimes pointing nearly straight up, sometimes leaning far over. Those swings change its seasons completely. Earth avoids that fate because its moon is large enough to act as a gyroscope, holding the planet's orientation steady as it spins. It's another gift from collision, a product of violence that ensures stability. If you think about it, every smooth, predictable movement we experience, the turning of the Earth, the pattern of seasons, the gentle tug of tides, is balanced on the outcome of those ancient impacts. Without them, the rhythm of life would be unrecognizable. The day might last hours or months. The sun might rise in strange shifting arcs across the sky. There might be no moon to light the night, no tides to stir the oceans. It's a reminder that the conditions we take for granted are anything but ordinary. They are the survivors of chaos, frozen into balance by time. The idea of angular momentum, that motion continues unless interrupted, means that every spin, every tilt, every wobble from those ancient days still exists in some form. They're blended together in the smooth, stable rotation we now feel as constant. It's not truly constant. It's the cumulative product of billions of tiny variations that have averaged out into harmony. Each impact added a note, and over eons those notes formed a steady rhythm. The Earth we know is the symphony that came from it. If we could compress all of that history, from the first collision that began the spin to the one that formed the moon, into a single scene, it would be hard to believe it ended with something as calm as our modern planet. Imagine it, a glowing, molten world surrounded by vapor, struck again and again by incoming bodies, each explosion lighting the dark with a brightness that could be seen across the solar system, and then slowly the fire fading, the impacts growing rarer, the surface hardening, oceans forming, clouds gathering. The same world that once shook and boiled into new shapes now turns quietly, carrying forests, cities, and oceans, its violent origins hidden beneath the stillness we feel today. That stillness is deceptive, of course. The Earth's rotation carries traces of every collision it survived. The slight tilt that makes one hemisphere bask in sunlight, while the other cools, the gentle tug of the moon, the precise length of a day, all are echoes of that time. The collision stopped, but their effect didn't. They're built into the structure of the planet, written into the laws of motion that keep it turning. What makes this story even more extraordinary is that the same process is happening elsewhere right now. In distant star systems forming across the galaxy, other young planets are colliding, merging, and spinning into stability. Their futures are being written in the same language of gravity and motion that shaped ours. Somewhere, billions of kilometers away, another world is enduring its own series of cosmic bumps, and someday it may settle into its own smooth spin. If intelligent life ever arises there, it might look up at its sky and ask the same question we're asking tonight. Why does our world spin? And the answer would be the same. Because it began that way. Because motion never stopped. Our own planet is a monument to that principle. Every mountain and wave moves with it. Every human life unfolds beneath it. The calm we experience is built on the memory of impacts, each one a chapter in a story written long before there were eyes to see or minds to wonder. The collisions gave us the tilt, the moon, the rhythm. The rest has been refinement, motion settling into grace. The Earth still turns, carrying the scars of its past invisibly beneath its crust, its rotation unbroken, its balance maintained. The next time you watch the sky at night and see the moon glowing softly above the horizon, remember that you're looking at the outcome of a collision that changed everything. The light that bathes your world in silver was born from impact, from the chaos of beginnings. Yet here it is, steady, reliable, serene. The planet spins below it, the tides rise to meet it, and time moves forward in a rhythm that began in fire and dust. The quiet turning of the earth is not the absence of chaos. It's what remains after chaos found its balance. When you wake in the morning and see light spilling softly through the window, what you're really seeing is movement. Not the sun moving through the sky, though that's how it appears, but the turning of the earth itself. Every sunrise, every fading twilight, every shadow that slides across a wall is the product of the same slow rotation that began billions of years ago. The rhythm of day and night is the most familiar pattern in our lives, but it's also one of the most remarkable, the visible consequence of our planet spinning through the endless dark. If you could float above the Earth and watch it from space, you would see half the planet bathed in sunlight and half veiled in shadow. That line between light and dark is called the terminator, and it's always moving. It glides endlessly around the world, dividing day from night, sweeping across continents, oceans and clouds. Every moment somewhere, dawn is beginning, and somewhere else, night is falling. It never stops. It never slows. It's the living boundary between warmth and cold, brightness and calm. What's so striking about this motion is how perfect it feels from our perspective. The sun appears to rise in the east, reach its highest point and sink into the west with such regularity that we use it to measure time. But the sun isn't really moving around us, we're rotating toward it. Our world turns eastward, so the sun seems to travel westward across the sky. It's an illusion so natural that it took humans thousands of years to recognize it. Our senses tell us the earth is still and the heavens revolve, but the truth is the opposite. We are the ones moving. Every dawn is a place on earth turning once more to face the sun. At the equator, the surface moves faster than at any other latitude, about 1,670 kilometers per hour. That means someone standing there experiences sunrise and sunset more quickly than someone near the poles. The rotation defines not just the pattern of light and dark, but also how it feels, how long the transitions last, how the shadows stretch and fade. The geometry of our spin creates the way sunlight behaves, shaping the character of mornings and evenings all over the planet. For most of us, it's easy to forget that what we call day and night are not universal. They depend entirely on where you are on the globe and how the planet is tilted. At the poles, the rhythm breaks down completely. There are months of light and months of darkness because of the way Earth's axis leans relative to the sun. In the equatorial regions, the days and nights are nearly equal year-round. Everywhere else, they stretch and shorten as the planet orbits. That variation is one of the defining features of life on Earth. It gives us seasons, migrations, sleep patterns, and the feeling of time passing through cycles rather than in a straight line. That slow alternation of light and shadow has shaped every organism that ever lived. Even the simplest bacteria respond to it. They've evolved to anticipate dawn and dusk, adjusting their metabolism to make use of sunlight or to protect themselves from it. Plants open and close their leaves based on the rotation of the planet, aligning their rhythms with the day's light. Animals wake, hunt, feed, or rest in patterns dictated by the same turning motion. The entire biosphere is synchronized to a planet's rotation, a living clockwork driven by the spin that never stopped. In humans, that rhythm lives deep inside. Each of us carries an internal clock, the circadian rhythm, tuned to roughly 24 hours. It's built into our genes, our hormones, and even the structure of our brains. It doesn't need a watch or a calendar. It evolved because the cycle of light and dark is the most consistent environmental signal we've ever known. When light hits our eyes in the morning, it resets that internal timer, signaling the body that it's time to wake, to be alert, to move. As the light fades, the brain releases melatonin, telling the body it's time to rest. Even if you could somehow block out all light and live in perfect darkness, your internal rhythm would still hover close to a 24-hour cycle. That's how deeply the Earth's spin is written into biology. What's fascinating is how seamlessly this cosmic motion translates into something as intimate as sleep. When you close your eyes at night, you're not just resting, you're aligning with the planet's rotation. You sleep while your part of the Earth faces away from the sun and awaken when it turns back toward it. Your body, your thoughts, your sense of time, all are connected to that vast turning motion beneath your feet. You might never feel it directly, but you live entirely within its rhythm. Imagine standing outside just before dawn. The sky is pale and still, a quiet gradient from black to blue. Birds begin to stir and the air feels different, cooler, lighter. That change isn't in the sky itself, but in your position relative to the sun. The Earth is carrying you toward the light, turning smoothly and silently. Within minutes, the first rays slip above the horizon, touching trees, roofs, and faces. The entire world brightens as your side of the planet moves into sunlight. By midday, you're facing the sun directly. Then slowly, the angle changes again. Shadows lengthen, colours warm, and evening approaches. You're moving back into the shadow half of the planet. It feels like the sun is leaving, but it's you turning away. That perspective, realizing the light doesn't move across us but that we move through it, changes the way you think about time. Each day isn't a repetition but a rotation. Every sunrise is a return, every sunset a departure, every night a half-turn deeper into space. And though it happens constantly, you're always on the surface, moving with it. You've been rotating since you were born. The room you sleep in, the bed beneath you, the air in your lungs, all of it moves with the same smooth spin that defines a day. The alternation of day and night also shapes the planet's atmosphere. The sun heats one side, causing air to expand and rise, while the other side cools and the air sinks. This constant pattern of warming and cooling creates global circulation, the great convection cells that drive weather and wind. Without the rotation, the difference between day and night would still exist, but the air wouldn't flow the same way. The spin introduces the Coriolis effect, curving winds into spirals, creating trade winds and jet streams. The interplay between rotation and sunlight turns the atmosphere into a living system, in perpetual motion, mirroring the spin that drives it. Even the oceans dance to the same rhythm. As the surface warms under sunlight and cools under nightfall, layers of water mix and circulate. The rotation, combined with the gravitational pull of the moon, creates tides that rise and fall in a complex choreography with the day-night cycle. The sea moves rhythmically because the planet turns rhythmically. It's all part of the same pattern. For early humans, the movement of light and shadow was one of the first ways to measure time. Long before clocks, people watched the shifting sun and learned to predict its return. They built monuments aligned with sunrise and sunset, tracking solstices and equinoxes. The rhythm of day and night became the foundation for calendars, agriculture, and ritual. It gave structure to life, to labour, to rest. To them, the sun's path across the sky wasn't just light, it was a measure of existence. That ancient sense of time still shapes us. Even now, in a world filled with artificial light, our bodies remember the old rhythm. The glow of a screen at midnight can confuse that ancient clock, keeping the brain in a state of daylight when the planet has turned to face the stars. That's why artificial light affects sleep. Our internal rhythms are tuned not to technology, but to the movement of the Earth itself. The body expects darkness when the world turns away from the sun, and when it doesn't find it, the balance falters. It's easy to think of day and night as opposites, one for activity, the other for rest. But they're really two sides of the same motion. They define each other. Without darkness, light would have no meaning. Without day, night would lose its place. The rotation of the Earth makes both possible, giving life contrast and rhythm. Every creature, every ecosystem, every landscape is shaped by that alternation. No living thing escapes it. Even the deep ocean, where sunlight never reaches, follows cycles influenced by the planet's spin as pressure waves, tides, temperature shifts. The dance between light and darkness extends from the highest mountain to the deepest trench. When you see the stars emerge at twilight, they seem to rise slowly from the horizon, but in truth, they're not rising at all. The Earth is turning away from the sun, revealing the vast field of space behind it. Night is simply the shadow of the Earth projected onto the universe. It's not a separate realm, just the half of the world that faces outward, away from the light. When you stand under that dark sky, you're looking directly into space, shielded from sunlight only because the planet itself is between you and the star that sustains you. It's an extraordinary thought, that the blackness above you isn't emptiness, but the other side of the same motion that gives you daylight. There's a quiet symmetry in how that works. Half the planet is always bright, half always dark, and the boundary between them is always moving. The same line that brings dawn to one person brings dusk to another. The same sun that sets for you is rising for someone else. All of humanity, all life shares that rotation. It connects every place and every moment through the simple act of turning. That connection has always influenced the human imagination. We mark our days by the sun's apparent motion, but we also measure our lives by the feeling of light and dark. Morning symbolizes renewal. Night represents rest, mystery, or reflection. These meanings come not from the sun itself, but from how its light interacts with our turning world. Every culture, every language, has stories and rituals tied to this motion. Prayers at dawn, fires at dusk, festivals marking the longest and shortest days. The rotation of the Earth is the clock that underlies every calendar, every ritual of time. In the grand scale of the cosmos, it's a humble motion. One rotation every 24 hours, one spin among billions of others. Yet for us, it's everything. It defines how we live, how we sleep, how we think about beginnings and endings. The dance of day and night is the quiet heartbeat of the planet, marking time not with sound but with light and shadow. You don't feel it, but you see its evidence every time you glance at the sky. If you were to watch the Earth's surface from above, sped up through time, you'd see a breathtaking rhythm. The line of shadow sweeping across oceans, racing over mountain ranges, rolling across deserts and forests. Cities flicker to life as night falls and fade as dawn returns. Storms catch the last light of evening and glow faintly in the dark. It's a pattern so vast that you can only see it from space, a pulse of light and shadow circling endlessly, never repeating in exactly the same way, but always continuing. That pattern is the visible trace of our rotation, a living map of time passing. Every 24 hours, the Earth completes one turn and the entire cycle begins again. The sun doesn't move across our sky, we move through its light. And in that motion, everything we know, time, temperature, weather, even thought, finds its rhythm. The spin of the planet is the mechanism that turns light into time and motion into meaning. Without it, the world would be frozen in eternal day on one side and endless night on the other. The dance would stop. Life, as we know it, would have nowhere to exist. What makes this so extraordinary is how natural it feels. The rotation is invisible, effortless. We never sense the speed or the scale of it. We simply live within its effects, waking, working, sleeping, dreaming, as the planet carries us from sunlight into starlight and back again. The Earth's spin is not just a physical fact, it's the foundation of our experience. It gives us the shape of time itself. And yet, even this steady motion changes, though so slowly that no lifetime could notice it. The rotation is gradually slowing, lengthening the days by fractions of a second over centuries. In distant ages, when the days were shorter, the dance of light and shadow moved faster, the rhythm of life slightly different. As time passes, the steps of that dance stretch out. The planet's spin is evolving, the tempo shifting almost imperceptibly, but the pattern endures. The alternation of day and night remains, unbroken, continuous, eternal on a human scale. When you stand in sunlight or lie awake at night watching the faint glow of stars, you're part of that same movement. You're not beneath the sky, you're inside a motion that never ceases. Every second you're being carried eastward, turning through light into darkness and back again. The entire experience of living on Earth is defined by that silent, graceful revolution. And as the planet turns, the rhythm it creates, this endless alternation of day and night, becomes something more than just the passing of time. It becomes balance itself. Light and darkness, energy and rest, motion and stillness, all intertwined in one continuous cycle. The same spin that began in chaos now writes the pattern of peace we live by. Somewhere right now, the first light of morning is touching a distant horizon. Somewhere else, night is falling. The line between them slides across the surface of the planet, unhurried, eternal. It has done so for billions of years and will continue long after we're gone. The dance of day and night never ends. It only moves, gracefully, quietly, forever turning with the world that spins beneath it. The Earth feels timeless as it turns. Each sunrise seems identical to the one before. Every evening fades at the same familiar pace. The days appear constant, measured and reliable, as though the planet's rhythm were carved into the universe itself. But it isn't. Beneath that sense of permanence, the rotation is changing. Slowly, invisibly, the Earth is losing speed. The days are lengthening, not by minutes or hours, but by fractions of a second spread across centuries. The planet's spin, once far faster than it is now, is gradually winding down. That slowing is so subtle that no living thing could ever feel it. Even the most precise clocks can only detect it through generations of careful measurement. Yet it's happening all the time, as steady as the rotation itself. The Earth spins slightly slower today than it did yesterday, and it will spin a little slower tomorrow. The cause is simple in concept, but immense in scale. A transfer of energy between the Earth and its companion, the Moon. When you stand at the edge of an ocean and watch the tide rise, you're seeing this process unfold. The tides are the direct link between the planet's spin and its gradual slowing. They're not just the movement of water, but the expression of gravitational tension, the pull of the Moon stretching the Earth itself. As the Moon orbits, its gravity pulls on the oceans, raising bulges of water on the side facing it and the side opposite. Those bulges aren't perfectly aligned with the Moon, because the Earth is spinning faster than the Moon moves around it. The rotation carries the bulges slightly ahead of the Moon's position, and that offset creates friction. A drag between the planet's spinning surface and the gravitational pull of the tides. That drag acts like a brake. Energy from Earth's rotation is converted into heat through friction in the oceans and the crust. Tiny amounts of that energy are also transferred to the Moon, pushing it slightly farther away in its orbit. It's a subtle, continuous exchange. Earth slows down a little, and the Moon drifts outward a little. The two have been locked in this slow gravitational dialogue for billions of years. When the Moon first formed, it was much closer, maybe only 20,000 kilometers away, compared to the 384,000 kilometers today. From the surface, it would have looked enormous, looming bright and large in the young sky. Back then, days on Earth were only about 6 hours long. The tides were massive, sweeping across the surface with incredible force, reshaping coastlines and stirring the oceans. Over time, the friction of those tides drained energy from the planet's spin, lengthening the day and moving the Moon outward. The pace of that change is glacial but relentless. On average, a day lengthens by about 1.7 milliseconds every century. That means that since the time of the dinosaurs, the day has grown by roughly half an hour. In human terms, it's almost nothing. You could live 100 lifetimes and never notice a difference. But in the language of planetary time, it's significant. It means that the Earth's spin, once fast and fiery in its youth, is gradually calming, like a wheel coasting towards stillness. Stillness, though, is not something that will ever truly arrive. The forces involved are far too gentle and too evenly balanced for the planet to stop turning completely. The slowing will continue, yes, but it will eventually reach a point of equilibrium. The Moon's outward drift will continue until its orbit, and the Earth's rotation becomes synchronized, until one side of the Earth always faces the Moon, just as one side of the Moon always faces us. When that happens, the Earth's rotation and the Moon's orbit will share the same period, locked together in mutual stillness relative to each other. But that outcome lies billions of years in the future, long after the Sun itself has changed beyond recognition. For now, the slowing remains one of those quiet facts about the world that most people never think about, but it influences more than we realize. The extra fraction of a second added to the day affects timekeeping in small but measurable ways. Astronomers and physicists have to account for it in their observations. Every so often, we add what's called a leap second to our official clocks to keep them aligned with Earth's actual rotation. Atomic clocks, which are unimaginably precise, don't slow down, but the planet does, and the difference accumulates. It's a strange reversal. We now have to adjust our sense of time to match a world that's changing beneath us. Even more intriguing is that this slowing isn't perfectly smooth. The Earth doesn't turn like a rigid sphere. It's flexible, elastic, layered. The crust floats over a molten mantle, and the core spins at a slightly different rate. These inner dynamics create tiny fluctuations in rotation speed. Earthquakes, melting ice caps, shifting ocean currents all redistribute mass, and that redistribution changes how the planet spins. It's the same principle as a figure skater moving their arms. When mass moves closer to the axis, rotation speeds up slightly. When it moves away, it slows down. That's why large-scale events like major earthquakes can alter the length of a day by microseconds. It's imperceptible, but measurable. The planet is constantly adjusting itself, balancing mass, conserving momentum. The slowing of Earth's rotation has shaped the evolution of life itself, though we rarely consider it. The length of a day determines the rhythm of light and darkness, which influences biological cycles. Early organisms on a rapidly spinning planet experience shorter days, faster changes in light and temperature. As the rotation slowed, those cycles lengthened, allowing life to adapt to a gentler rhythm. Photosynthesis, metabolism, and behavior all evolved within that gradually stretching day. The biology of life and the physics of the planet have been intertwined since the beginning. In that sense, the slowing spin isn't just a physical fact, it's part of a story of balance. Every bit of energy lost to tidal friction becomes part of another process. The Moon's motion, the stability of the Earth's tilt, the predictability of tides. Nothing is truly lost, it's simply redistributed. The slowing of rotation gives something back: regularity, order, and the stable conditions that made complex life possible. What's remarkable about this process is how steady it has been. The Moon moves outward by about 3.8 centimeters each year. That may sound insignificant, but it's enough that, in the very distant future, it will no longer perfectly cover the Sun during eclipses. The eclipses we see today, where the Moon's disk fits neatly over the Sun, are temporary, a coincidence of scale that will eventually fade. As the Moon retreats, its apparent size in the sky will shrink, and the world will lose that perfect symmetry. Even phenomena of great beauty carry the signature of the planet's slowing spin. When scientists study ancient corals and sediments, they can see this change recorded in the natural calendar of the Earth. Some species of coral build daily growth rings, much like trees. By counting those rings in fossils hundreds of millions of years old, researchers can calculate how many days fit into a year at that time. The result shows that long ago, the year, which depends on the Earth's orbit around the Sun, was the same length, but there were more days in it. Around 400 million years ago, for instance, a year held roughly 400 days, which means each day was just over 21 hours long. The evidence is literal, physical, carved into the skeletons of creatures that lived in warm, shallow seas when the world's rotation was faster. Those rings, laid down day by day, are the quietest testimony imaginable to the planet's slowing. They're fossils of time itself, a biological record of the changing pace of the Earth's spin. It's humbling to think that something as small as a coral polyp could hold evidence of a process stretching across billions of years. The tiny variations in those layers tell a story that began when the moon was still close enough to pull tides that swept across entire continents. It's easy to imagine the Earth's rotation as fixed, but in reality, it's a delicate balance between motion and resistance. The atmosphere exerts drag on the surface, the oceans tug against the seabed, the moon and sun pull on the planet's mass, and the molten interior shifts under its crust. Each of these interactions extracts an infinitesimal amount of energy. Over vast stretches of time, those infinitesimals add up. The result is a rotation that, though stable, is not static. The small variations we can measure today reveal how interconnected everything is. When air pressure changes globally, when water moves from ice caps to oceans, when magma shifts in the mantle, the Earth's moment of inertia changes slightly. These changes ripple through the rotation. The same physics applies to satellites and spacecraft, which must account for Earth's exact spin when navigating. The slowing of the planet might be subtle, but its fingerprints are everywhere. In astronomy, in navigation, in timekeeping, even in climate patterns. Over the lifetime of the solar system, this process has created a kind of equilibrium. The fast, chaotic spin of the planet's youth has given way to a slower, more orderly motion. The tides are gentler, the days longer, the balance steadier. The slowing spin has stabilized the Earth's tilt, helped regulate its climate, and kept its rhythm predictable enough for life to adapt. It's as though the planet found a sustainable pace, a tempo that could support oceans, weather, and growth without tearing itself apart. That balance won't last forever, but on human timescales it might as well. The slowing is so slow that millions of generations could come and go without noticing it. The constancy of our days and nights is one of the most reliable facts of existence. The world turns, and though the turning changes, it changes so gently that the difference is absorbed into the flow of life. The slowing spin is not a sign of decay but of maturity. The planet has settled into its natural rhythm, shaped by its interactions with the moon and the physics of motion itself. If you look at the sky and see the moon glowing softly above the horizon, you're watching that process continue. Its light, reflected from the sun, carries the memory of its origin, the same impact that set this exchange in motion. The moon pulls on the oceans pull back, and the balance between them governs the speed of the Earth's rotation. Every tide that rises and falls transfers a little energy outward, adjusting the rhythm of the world. It's the most delicate conversation in nature, spoken in gravity, continuing endlessly. Even though the Earth is slowing, it's not becoming unstable. The energy lost is tiny compared to the energy the planet holds in its motion. The angular momentum of a rotating sphere the size of Earth is immense, roughly 7 x 10 33 kilogram meters squared per second. To slow it by even a small fraction takes billions of years. The planet could spin for countless eons before reaching any meaningful change in its day length. That sheer scale of stability is why we experience time as constant. The planet's gradual slowing doesn't disrupt our lives, it defines them. If you could somehow stand on the surface of the Earth billions of years from now and measure a single day, you'd find it significantly longer. The sun would still rise and set, but the cycle would move at a slower tempo. The moon would hang slightly farther away, smaller in the sky. The tides would be weaker, the pull between the two worlds less intense. Yet the basic pattern, rotation, revolution, balance, would remain. The slowing is part of that pattern, a natural extension of the same forces that began it. There's something deeply peaceful about that realization. The Earth doesn't resist its slowing, it simply evolves. The friction that tugs at its spin is the same friction that warms its oceans and drives its tides. The loss of speed is not a failure of motion, but a continuation of it. The universe values balance, not haste. The planet turns a little slower each day, and in doing so maintains harmony with the forces around it. Every second that passes carries the faintest trace of that deceleration, but it's too small for us to sense. Our clocks, our bodies, our hearts, all move within the same rhythm, synchronized to the planet's spin. The slowing is not something to notice, it's something to trust. It means that gravity is still doing its work, that the moon still circles above, that the laws of motion still hold true. And as the planet continues its long, slow rotation, each fraction of a second added to the day becomes part of the quiet continuity of time. The Earth turns a little more gently than before, the moon drifts a little farther, and the tides keep their rhythm. The change is imperceptible, yet absolute. In that gradual slowing lies the proof that motion is eternal, but never static. The Earth's spin has lasted for billions of years, and it will last for billions more. It may slow, it may shift, but it will never stop. The subtle slowing is not the end of movement. It's the reminder that even the most constant things in the universe evolve, slowly, silently, beautifully, as they turn. The moon doesn't seem powerful when you look at it. It hangs in the sky like a pale lantern, silent and still. Its light is soft, its presence constant, almost delicate. But that quiet companion, drifting through its endless orbit, is exerting a force so steady and immense that it shapes the motion of our entire planet. It pulls at the oceans, it slows the Earth's spin, it stabilizes our axis. Everything it does happens slowly, invisibly, without sound or vibration. Yet its influence reaches into every tide, every rhythm, every rotation. The moon's gentle tug governs much of what makes Earth the world we know. If you stand on a beach and watch the tide rise, you're seeing gravity in action across a scale that's hard to imagine. The moon's pull on the Earth is strong enough to lift entire oceans. It stretches the planet itself, drawing water slightly toward it on the side facing the moon and, paradoxically, on the side facing away as well. That second bulge happens because the Earth, pulled more strongly than the far side water, moves slightly toward the moon, leaving the far side water behind. The result is two simultaneous tides, one beneath the moon, one opposite it. As the Earth spins beneath these bulges, coastlines experience the regular rise and fall of the sea. This pattern happens every day, twice a day, everywhere the ocean meets land. It's so familiar that it feels like part of nature's design, but it's really an ongoing consequence of the Earth-Moon interaction. The gravitational pull between the two bodies has been the same since their shared origin, but the way it plays out changes over time. Because the Earth spins faster than the moon orbits, the tidal bulges don't stay directly aligned with the moon. The planet's rotation drags them slightly ahead. That offset means the bulges pull forward on the moon's orbit, transferring a tiny amount of energy outward. In return, the moon's gravity pulls backward on the bulges, slowing Earth's rotation. The result is a constant exchange of energy, a gravitational dialogue that has lasted for billions of years. The moon gains orbital energy, drifting slowly away at about 3.8 centimeters per year. The Earth loses rotational energy, its spin gradually easing. Both changes are minuscule on human timescales, but immense across geological time. The moon we see tonight is not in the same place it was when the first life appeared on this planet. It's receded by tens of thousands of kilometers since then, its orbit expanding, its pull adjusting. And though we can't feel it, that gentle tug has reshaped the planet's history in countless ways. The tides are the most visible result, but their influence extends far beyond the shore. Tides stir the oceans, circulating nutrients, mixing temperatures, and sustaining marine life. They help drive currents that redistribute heat across the planet. Without the moon's pull, the oceans would still move, driven by wind and rotation, but they wouldn't breathe in the same way. The regular rising and falling of the sea is a kind of planetary heartbeat, one that oxygenates the water, nurtures ecosystems, and keeps coastal regions alive. For billions of years, that heartbeat has been steady, its pulse guided by the moon. In the planet's early days, when the moon was much closer, the tides were enormous. Water may have surged hundreds of meters high in some regions, sweeping across continents and retreating again. The friction generated by those immense tides helped warm the planet and mix its oceans. Over time, as the moon moved farther away, the tides became gentler, and the Earth's rotation slowed. The violent rhythms of the early world gave way to the calm cycles we know now. The moon, by leaving, was also soothing. Even today, the Earth's shape is not completely solid or still. The crust flexes slightly under the moon's pull. Mountains rise and fall by a few centimeters as the planet breathes under tidal forces. The mantle shifts, the oceans swell, the atmosphere responds. The entire Earth moves to the moon's rhythm, every part of it tied to that gravitational connection. It's as if the planet itself is dancing slowly and gracefully to a silent music that began when the two worlds were born. The moon's influence doesn't stop with the tides. Its presence has also stabilized the tilt of Earth's axis, the invisible line around which the planet spins. That tilt, about 23.5 degrees, is what gives us seasons. Without the moon, the Earth's tilt would wobble unpredictably under the gravitational influence of the sun and other planets. Over millions of years, it might swing wildly, changing from almost upright to heavily tilted. Those shifts would create extreme climate swings, alternating between frozen ages and searing heat. Mars, which lacks a large moon, experiences just that. Its tilt can vary by tens of degrees, transforming its weather and atmosphere over time. Earth avoids that fate because the moon's gravitational pull acts like a stabilizer, keeping the tilt steady within a narrow range. That stability has been crucial for life. It's given the planet a predictable climate, a balance of light and dark, a reliable cycle of seasons. Over billions of years, evolution has unfolded within that consistency. The moon's quiet pull, by preventing chaos in the planet's orientation, allowed continuity in everything from photosynthesis to migration to the patterns of rainfall. Without that steadying influence, the Earth's environment might have been too erratic for complex life to develop and persist. The moon, small as it seems, is one of the reasons our world is livable. There's a deep interdependence in that relationship. The Earth gave birth to the moon, but the moon, in turn, shaped the Earth's destiny. The collision that created it, when the young Earth was struck by Theia, not only altered the planet's rotation and tilt, but created the gravitational partnership that has endured ever since. The fragments thrown into orbit coalesced into a sphere that became a companion, a regulator, and a mirror. That single event set into motion a chain of effects that continues in every tide, every gentle deceleration of the planet's spin. When you think about how large-scale that relationship is, it's almost impossible to grasp. The moon weighs about 1/80th of the Earth, yet its gravitational reach extends across an entire world. It lifts oceans, steadies climates, and dictates the rhythm of time. It does all this without engines, without sound, just through the geometry of mass and distance. It's one of the purest demonstrations of how gravity works. Simple, absolute, constant. If the moon suddenly vanished, the immediate effect wouldn't be catastrophic in the way movies imagine, but it would be profound. The tides would weaken drastically, driven only by the sun's lesser influence. Coastal ecosystems would falter. The Earth's tilt would begin to wobble slowly, leading to unpredictable shifts in climate over tens of thousands of years. The nights would grow darker, the rhythm of life less stable. the delicate equilibrium we now experience would begin to unravel. It's hard to overstate how much of our planet's identity is tied to that single grey sphere in the sky. Astronomers have long known that the moon's recession, its slow drift outward, is a continuous process. Laser reflectors placed on the lunar surface by Apollo astronauts allow us to measure the distance with centimetre precision. The data confirms what theory predicted. The moon is moving away. The Earth's day is lengthening. The relationship between the two bodies is still evolving, just as it has since their shared beginning. It's a reminder that even the most stable-seeming motions in the universe are dynamic. Nothing stays perfectly fixed. Everything interacts, transfers, adjusts. That interplay of forces also creates smaller phenomena, some of which we can measure and even feel indirectly. Tidal friction doesn't just slow the Earth's spin, it slightly deforms the crust, producing tiny but measurable energy releases. It affects how the planet's rotation wobbles around its axis, a motion known as nutation. It can even influence how the liquid iron in the outer core circulates, subtly modifying the magnetic field. Every part of the planet feels the moon's touch, from the deepest layers to the outermost atmosphere. In that sense, the moon's tug isn't just a physical force, it's part of a system of interlocking movements that make the Earth what it is. The rotation of the planet, the orbit of the moon, the pull of the tides, the shape of the oceans, they all belong to the same interconnected dance. Each depends on the others, each is balanced against the rest. The moon doesn't simply orbit us, it participates in our motion, guiding it, refining it, shaping it in ways so slow and subtle that we call them eternal. It's strange to think that this same gravitational relationship has been visible in the sky for as long as there have been eyes to see it. Early humans watched the moon rise and fall, wax and wane, and saw in it patterns of renewal. Long before they understood gravity, they knew the moon controlled the tides. They saw that it governed the rhythm of the sea, and by extension the rhythm of their own lives. The lunar month became one of humanity's first measures of time, a natural cycle that matched the planet's rotation and the movement of the sun. Without realizing it, they were observing the same exchange of energy that scientists measure today, the same gentle tug that shapes the planet itself. That sense of connection still lingers. The moon feels familiar, intimate, even though it's 384,000 kilometers away. Its light reaches us about a second and a half after it leaves the surface, but its gravitational pull acts instantly, in the same moment, binding us to it. Every ripple on the ocean, every tide that creeps across the sand is part of that connection. When you stand by the shore and feel the tide pulling at your feet, you're part of that gravitational relationship too. The earth, the water, and you're all moving together under the same invisible influence. What's remarkable is how balanced it all is. The moon pulls on the earth pulls on the moon, and the result is harmony. The moon keeps its same face turned toward us because it too has become locked by the same forces that are slowing the Earth. Its rotation matches its orbit. It spins once every 27.3 days, the same time it takes to circle the planet. That's why we never see its far side from Earth. Not because it doesn't rotate, but because it rotates perfectly in step with its revolution. The same gravitational mechanism that's slowing Earth has already completed its work on the moon. That tidal locking gives us the familiar view we've seen for thousands of years. The same craters, the same patterns of light and dark, always facing us. The moon's far side, unseen from Earth, is another world entirely, but it follows the same rhythm. It's a demonstration of how gravity creates order out of motion. Two bodies, bound together, eventually fall into synchronization. It's the universe's way of conserving energy while maintaining balance. The Earth, in its turn, is on the same path, though it will take billions of years to reach it. Someday, far beyond the lifespan of our civilization, the Earth will rotate once for every orbit the moon completes. The same hemisphere will always face the moon, and the length of a day will match the lunar month. When that happens, the exchange of energy will stop. The system will have reached equilibrium. There will be no more slowing, no more drift, just two worlds turning together, locked forever in silent partnership. That far future, though unimaginable in scale, is an extension of what's happening right now. The tides we see are the visible signs of that journey. They're small movements in a vast cosmic process, the whisper of gravity continuing its slow, patient work. Every wave that breaks, every rise and fall of the ocean is a fragment of that long story. It's a gentle reminder that motion is always shared, always connected. The moon's tug may be invisible, but it's everywhere. It shapes the pull of gravity we feel, the length of the day we live through, the rhythm of the world we inhabit. It's a force that asks for nothing and never rests. It acts with perfect consistency, moving oceans, guiding the tilt of the Earth, keeping the planet's spin in graceful control. When you look up at night and see the moon suspended above you, you're looking at something far more than a bright circle in the dark. You're seeing a partner in motion, a reminder of balance, a quiet companion that has been influencing this world since before there were oceans deep enough to hold tides. It's the gentlest of forces shaping the grandest of movements, the invisible hand that steadies a spinning world. If the Earth were perfectly symmetrical, perfectly smooth and perfectly balanced, its spin would be constant and unwavering, like a flawless gyroscope turning in endless equilibrium. But the world isn't perfect. It's lopsided, layered, alive with motion inside and out. Its shape is stretched at the equator, its crust shifts, its mass redistributes with every wind, wave and quake. And because of all this, the planet doesn't just spin, it wobbles, slowly, subtly, predictably it sways as it turns, tilting and adjusting in ways too faint to feel, but large enough to change the sky above us and the pattern of seasons below. That wobble, known as precession, is one of the Earth's quietest movements. It happens so slowly that it takes about 26,000 years for a single cycle to complete. Over that time, the direction of the planet's axis gradually traces a circle in space, like the slow turning of a spinning top. The North Pole points toward one star now, but in the distant past it pointed elsewhere, and in the distant future it will again. Today we call that star Polaris, the North Star, because it happens to sit almost exactly above the pole, but that's only temporary. Thousands of years from now another star will take its place, as the axis slowly wobbles along its ancient path. The cause of this movement lies in the same forces that keep the Earth stable: gravity, the moon, and the sun. Because the Earth isn't a perfect sphere, but slightly bulged at the equator, the gravitational pull from both the sun and the moon acts unevenly on it. Those tugs try to straighten the tilt, to pull the equator into alignment with the plane of the orbit. But rather than flipping upright, the spinning planet responds in the way all rotating bodies do under torque. It precesses. The axis begins to move in a slow, circular pattern. It's a graceful compromise between balance and instability, a constant negotiation between the pull of gravity and the momentum of rotation. You can picture it easily if you've ever watched a spinning top. When it first begins to spin, it stands upright, steady and swift. As it slows, it starts to tilt, and its top begins to circle around an invisible point. That circling motion is precession. The Earth does the same, but its slowing is only partial. It's still turning fast enough to stay upright, but the gravitational pulls acting on its bulge give it that slow, sweeping motion of the axis. The difference is in scale. Where a top might wobble once per second, the Earth's axis takes tens of millennia to complete one rotation of its own. This slow wobble has a quiet but profound effect on the planet. It changes the orientation of the Earth's tilt relative to the Sun, shifting where sunlight falls most directly during different parts of the year. That means the timing of the seasons, over thousands of years, gradually drifts. The northern hemisphere's summer today occurs when Earth is farthest from the Sun. But in about 13,000 years, that relationship will reverse. Summers will occur when Earth is closest to the Sun, making them slightly warmer, winters slightly colder. The rhythm of the seasons remains the same, but the phase of that rhythm moves through time, cycling endlessly in this great astronomical clockwork. This pattern is one of several long-term variations in Earth's motion that shape climate over geological timescales, together with changes in the shape of Earth's orbit, known as eccentricity, and small oscillations in the angle of the tilt itself, called obliquity. Precession contributes to what scientists call the Milankovitch cycles. These cycles drive the slow waxing and waning of ice ages, altering how sunlight is distributed across latitudes over tens of thousands of years. The wobble of the planet isn't just an abstract motion in space, it's part of the deep pulse of climate, influencing glaciers, sea levels, and ecosystems across epochs. Yet even as it changes climate patterns over vast timescales, the wobble is so subtle that for all practical human experience, it's invisible. No one alive will ever see the axis shift enough to notice. The stars appear fixed, the seasons stable, the constellations eternal. Only precise measurements over centuries reveal that the sky is slowly turning in ways too slow for the senses. The ancient Egyptians, who built the pyramids aligned with the stars of their time, would find their celestial markers slightly misplaced if they could look up today. What feels permanent to us is actually a slow motion we live entirely within, a motion we inherit but never perceive. The moon plays a major role in how gentle that wobble is. Its gravitational pull stabilizes the tilt, keeping it within a narrow range. Without the moon, the wobble could have been far more extreme, swinging by tens of degrees and creating chaotic variations in climate. Mars offers a glimpse of what that might look like. Its small moons are too weak to steady it, and its axis can shift by up to 60 degrees over millions of years. The result is a world where seasons come and go with unpredictable intensity, where polar ice can melt completely or grow enormous, where equatorial regions freeze and thaw in cycles that defy pattern. Earth, by contrast, moves through time like a balanced top, steady enough for life to adapt, but dynamic enough to change slowly, giving evolution room to breathe. The Earth's wobble doesn't move only through space, it resonates through everything tied to timekeeping and orientation. Astronomers, navigators, and engineers all account for it. The positions of stars used for mapping the heavens are corrected for precession. The coordinates of the celestial poles, the points where the axis meets the sky, are constantly updated. Modern measurements show that the wobble isn't perfectly regular either. There are smaller, overlapping motions, nutation, caused by the combined tugs of the moon and sun as they move in slightly changing planes, and polar motion, a minor wandering of the Earth's axis relative to its crust driven by shifting air masses, ocean currents, and even the movement of groundwater. These variations are tiny, often just a few meters at the poles, but they remind us that even the most stable motions are layered with complexity. It's humbling to realize that the ground beneath us is part of such a slow, grand oscillation. When you look at the stars and see them rise and set in predictable arcs, you're seeing a projection of the planet's spin at this particular moment in its long cycle. Thousands of years ago, those same stars rose and set along slightly different paths. Thousands of years from now, they will again. The entire sky is shifting slowly, though we're too brief to notice. Our calendars, our constellations, even the mythology of the heavens are all temporary, bound to the current orientation of a planet that is never truly still. The mechanics of this wobble are rooted in the same laws that govern all motion. The conservation of angular momentum ensures that when a rotating body experiences an external torque, it doesn't simply tilt or fall, it precesses. The direction and speed of that precession depend on the distribution of mass, the rate of spin, and the strength of the torque. For Earth, the torque comes from the gravitational forces acting on its equatorial bulge. The rate of spin provides the stabilizing gyroscopic effect. The mass distribution, including the core and mantle, determines how the planet responds. If the Earth's core were not partially molten, If it were solid all the way through, the precession would be slightly different. The fluid core allows a subtle decoupling between layers, introducing additional variations known as free core nutation, a kind of resonance deep within the planet. These internal and external motions are linked in ways scientists are still uncovering. The wobble of the axis can interact with the circulation of the molten iron in the outer core, which in turn generates the magnetic field. Over long timescales, these feedbacks might even influence how the field drifts or flips. The Earth's magnetism, its climate, its tides, its spin, they're all part of the same interconnected system of motion and balance. The wobble is just one of the quieter signals in that system, but it's a crucial one, keeping the overall rhythm stable. Even the most sensitive instruments on Earth can barely detect the axis shifting in real time, but over centuries astronomers have traced its progress through careful observation. Ancient star charts compared with modern data show that the celestial poles drift through the sky at a rate of about 50 arc seconds per year. That's less than the apparent diameter of the moon every hour. Imperceptible to the naked eye, but absolute. The cumulative effect over millennia reorients the heavens. Constellations shift. The meaning of north and south in the sky evolves. Human civilization, for all its permanence, has existed during only a small fraction of one precessional cycle. The stars we align our cities and telescopes to are simply temporary markers in an ongoing celestial movement. While precession operates over tens of millennia, smaller wobbles happen more frequently. The Earth's axis oscillates by tiny amounts over 18.6 years, a rhythm caused by the regression of the Moon's orbital nodes, the points where the Moon's orbit crosses the Earth's orbital plane. This 18.6-year cycle subtly affects tides, atmospheric pressure, and even climate patterns. Certain coastal regions experience stronger or weaker tides depending on where the cycle stands. Meteorologists studying long-term variations in rainfall and storm frequency often find echoes of this lunar-driven rhythm in their data. The wobble, in other words, isn't just a distant astronomical curiosity. It's connected to the weather we experience, the seas we cross, and the timing of patterns we barely recognize. All these layers of motion, from precession to nutation to polar wander, combine to make the Earth a dynamic, responsive planet. It's not a fixed stage on which life unfolds, it's an active participant in the story. The axis shifts, the crust moves, the oceans flow, the air redistributes mass, and all of it subtly influences how the world turns. We live in the balance point of these forces, experiencing stability that's really the product of constant microscopic adjustments. The Earth wobbles, but that wobble is part of its grace, part of what makes it resilient rather than fragile. If you were to stand at the North Pole and somehow watch the sky for millennia, you'd see the stars drawing slow circles, the pole itself tracing its path around the sky. Today Polaris sits nearly motionless above the horizon there, a steadfast guide for navigation and myth alike. But ancient travellers looked to different stars, and future explorers will do the same. Around 12,000 years from now, Vega, a bright star in the constellation Lyra, will be the new North Star. The entire sky will appear slightly shifted, though the planet's rotation, the alternation of day and night, and the cycle of the seasons will continue as always. The wobble changes our view, not our rhythm. On timescales far beyond imagination, this slow precession, combined with the other orbital variations, acts as a kind of cosmic metronome for climate. It modulates how much sunlight each hemisphere receives during its summer, controlling the advance and retreat of ice sheets. The record of these cycles is written in layers of sediment, in trapped bubbles of ancient air within glaciers, in the chemistry of ocean floors. Every few tens of thousands of years, the planet enters a new phase of this long oscillation, an ice age beginning, an interglacial warming, a reshaping of ecosystems and coastlines. These changes are vast, yet they're rooted in the same gentle wobble of the axis that shifts the pole stars in the night sky. It's difficult to comprehend that something as subtle as a tilt could alter the fate of continents, but that's the scale on which the Earth operates. The wobble is slow, patient, unstoppable. It doesn't announce itself. It simply keeps moving, millimetre by millimetre, guiding the rhythms of deep time. Every glacier that advanced, every desert that bloomed, every ancient shore that rose or fell has been touched by that motion. And still, in our own lives, it's invisible. The stars seem eternal, the seasons steady, the poles fixed. Our sense of permanence is a trick of scale. We live within a moving world that only feels still because its movements are vast and slow beyond our experience. The Earth wobbles as it spins, spins as it orbits, orbits as the solar system drifts through the galaxy. Layers of motion nested within motion. What feels solid is really the product of constant adjustment, of balance sustained through movement. The moon, once again, is the anchor in this dance. Its gravity doesn't stop the wobble, but it smooths it, taming what might otherwise be chaos into a long, graceful sway. The Earth's axis traces its slow circle under the moon's watchful influence, maintaining a stable tilt even as it precesses. The partnership between the two bodies, established in the violent impact that birthed them, has matured into something quietly elegant. A dynamic equilibrium that's lasted for billions of years. If you could somehow perceive time at that scale, if centuries felt like seconds, you'd see the Earth as a spinning top made of rock and ocean, swaying gently in sunlight, its axis looping slowly through space while the moon orbits around it. You'd see continents drift, ice expand and retreat, the glow of civilizations rise and fade, all beneath the slow, constant wobble that never stops. Its motion within motion, balance maintained through endless adjustment. And though we can't feel it, every sunrise, every night sky, every breath of wind happens within that movement. The wobble of the world is not something apart from us. It's the quiet background motion that defines the stability we depend on. The axis sways, the seasons drift, the stars change their places, but life continues, adapting to the rhythm of a planet that never truly stands still. The world wobbles, and in that wobble lies the secret of its endurance, a moving balance, an ancient rhythm, a motion so vast and gentle that it feels like stillness. There was a time when the passage of hours was not written in numbers, but in light. Before clocks, before calendars, before the idea of time as something that could be divided and counted, there was only the movement of shadows. Every day, as the sun crossed the sky, those shadows lengthened and shortened, tilted and turned, following the rhythm of the planet itself. People didn't yet know the Earth was spinning, but they lived by its rotation all the same. The world's first clock wasn't made of gears or hands or ticking metal. It was made of sunlight and stone. When you think about it, a shadow is the simplest possible proof that the Earth turns. As the planet rotates, the position of the sun in the sky changes, and the shadow cast by any object moves accordingly. In that movement lies the cycle of the day. Even before humans had words for physics or astronomy, they could see the connection between light and time. The sun rose, shadows appeared and crept along the ground, then faded as darkness returned. Every morning was a beginning, every evening an end. Time wasn't something you measured, it was something you felt. Eventually that feeling became observation. Ancient people noticed that shadows reached their shortest length when the sun was highest, and that this moment, when the light came straight down, happened at roughly the same point in every day. That moment became noon. By marking when a shadow pointed north or south, east or west, they began to divide the day. They were mapping the motion of the Earth without realizing it. The shadow became a pointer, and the sun became a clock face stretched across the sky. The first sundials were probably nothing more than sticks in the ground. Simple gnomons, as they came to be called later. As the sun rose and fell, the shadow of the stick traced a pattern around it, sweeping like the hand of a slow, steady clock. By studying that pattern, early astronomers could predict when the day would reach its midpoint, when the next sunrise would come, and how the seasons were changing. The sky became a calendar, and the Earth's rotation became something they could track with their eyes. It was a revelation born not from machines but from patience. The Earth turns at a constant rate, but that constancy isn't obvious unless you pay attention over long spans of time. Watching shadows was one of humanity's first ways of perceiving that constancy, the steady, unbroken rhythm of rotation beneath the changing light. It's possible that long before any civilization, people built stone markers or placed posts to follow the sun's path, using them to align with the seasons or to tell when to plant and harvest. Time, in the human sense, began when we noticed the sun did not move randomly. It followed a pattern, and that pattern came from the spinning of the ground beneath us. Many ancient structures still carry traces of that discovery. In Egypt, obelisks were raised not only as symbols of power, but also as monumental sundials. Their long, sharp shadows moved through the day, marking the division of time. In Mesopotamia, early astronomers carved shadow marks into stone, dividing daylight into hours long before mechanical timekeeping existed. In China, the oldest surviving sundial dates back more than 3,000 years, built to track the position of the sun at specific times of day. Across every culture, the idea appeared independently. The world's turning could be read in shadows. What's remarkable is that all these civilizations were measuring the same thing, the Earth's rotation, but they believed they were watching the sun's motion. To them, the sun was the one that travelled, the one that moved from east to west each day. It would take millennia before anyone realized the truth was reversed. Still, their measurements were astonishingly precise. The division of the day into 12 parts, the concept of hours, the tracking of seasons and solstices, all came from the movement of shadows. The very structure of modern timekeeping, the way we divide a day into hours and minutes, has its origin in the way sunlight shifts on the Earth's surface. For thousands of years, this simple method was enough. Shadows became the human way of seeing the planet's motion, of turning something vast and cosmic into something tangible and local. Every village, every temple, every city had its own measure of the sun. The angle of a shadow at midday told you what time of year it was. The length told you how far north or south you were. The speed told you how quickly the Earth was turning toward night. In watching those patterns, people were not just telling time, they were connecting themselves to the rhythm of the planet. Even as civilizations advanced, the principle stayed the same. The ancient Greeks refined sundials with geometry, carving hour lines to match the latitude of each city. They understood that the sun's height changed with the seasons, and they adjusted for it, realizing that time was not identical everywhere. The Babylonians used their keen astronomical records to predict the length of days and nights, noting how shadows behaved differently through the year. The Maya built observatories where sunlight would strike stones and temples at precise angles on solstices, aligning architecture with the turning of the Earth. Everywhere, people built their sense of order on the same invisible foundation, the rotation of the world beneath them. They might not have known what caused the motion, but they lived by it perfectly. Farmers planted by the light, sailors navigated by the sun and stars. Priests and scholars studied the shifting patterns of dawn and dusk to mark the calendar. All of them were measuring the Earth's spin, though none could feel it. It's humbling to realize how consistent that rhythm has been. The same spin that guided ancient farmers still guides satellites. The same rotation that made a shadow creep across a temple wall now powers atomic clocks and global positioning systems. The tools have changed, but the motion they measure has not. Timekeeping has become more precise, but it's still a translation of one thing, the rotation of the Earth, into something we can use and understand. Even now, when we talk about time zones, we're dividing the world by its rotation. Every 15 degrees of longitude corresponds to roughly 1 hour's difference between local noons, the time when the sun stands highest in the sky. The globe's division into 24 time zones reflects the planet's 24-hour spin. You can travel east and watch time advance, or travel west and watch it fall behind, because you're moving with or against the rotation. Every clock in every city on Earth is in its essence synchronized to the same motion that a stick in the ground once measured. The relationship between light, shadow, and time is still visible everywhere if you know how to look. Stand near a building on a clear day and watch how its shadow shifts. The angle tells you the hour. The direction tells you where you are on Earth. You can trace the planet's rotation in real time, in the way sunlight creeps across a wall or a field. The entire day's rhythm unfolds in that quiet motion. Every second you can see it, the world turning beneath the light. That connection between shadow and time runs deeper than science. It shaped how humans thought about existence itself. Light became a metaphor for life and knowledge, darkness for rest and mystery. Day and night, presence and absence became the framework for understanding the world. Those ideas came directly from the planet's turning, from the alternating dance of brightness and shadow. When early philosophers spoke of cycles, renewal and balance, they were describing what the Earth showed them every day. The endless repetition of rotation turned into meaning. As understanding deepened, the shadow's role evolved from symbolic to scientific. By the time of the ancient Greeks, astronomers like Eratosthenes used shadows to measure the size of the Earth itself. He noticed that at noon on the summer solstice in Syene, a vertical stick cast no shadow because the sun was directly overhead. But in Alexandria, farther north, the shadow had an angle. By measuring that angle and knowing the distance between the two cities, he calculated the circumference of the Earth with astonishing accuracy. From a single difference in shadow, he revealed the planet's size, proof that it was round, and a reminder that timekeeping and spatial understanding were born from the same phenomenon. Later, as mechanical clocks appeared, they didn't replace shadows, they imitated them. A sundial measures time by the rotation of the Earth. A clock does the same, but through gears instead of light. The pendulum, the escapement, the tick, all are mechanical shadows, converting the Earth's turning into human rhythm. Every clock on your wall is a miniature echo of that cosmic movement. Even now, when our most precise clocks use the vibration of atoms, they are still compared against the length of the day, still checked against the planet's rotation, because no matter how advanced our instruments become, time remains bound to that fundamental motion. In that sense, every clock is a map of the Earth's behaviour. It tells us not only what hour it is, but how consistently the planet spins. When astronomers compare atomic time with astronomical time, they can detect changes in rotation caused by the slowing of the Earth, the shifting of ice, the pull of tides. Modern timekeeping isn't just about precision, it's a way of listening to the planet. Every leap second added to our global time system is a small adjustment, a tiny acknowledgement that the world is turning slightly more slowly than before. The ancient sundial's shadow still falls, but now it's measured in microseconds instead of hours. What's fascinating is how the experience of time hasn't really changed. Whether you watched a shadow creep across stone or glanced at a glowing digital display, you're still witnessing the same motion expressed differently. Every second is a fragment of a rotation. Every minute is a step in the turning of the planet. Time feels abstract, but it's not. It's physical. It's the rotation of Earth converted into perception. If you were to strip away every clock, every calendar, every digital reminder, time would still flow exactly as it does now, marked by the movement of light and shadow. The sun would still rise, the shadows would still lean and stretch, the day would still move forward. The world's rotation is the one true clock that never needs winding, never needs repair. It has been keeping perfect time since long before humans appeared, and it will continue long after we're gone. Even in the age of satellites and atomic precision, we still live by that shadow. Farmers still depend on sunlight cycles, pilots still calculate flight times by longitude and rotation. Astronomers still measure motion in sidereal days, the time it takes the Earth to rotate once relative to the stars, slightly shorter than the solar day we live by. Our most advanced understanding of time still begins with the same observation. The planet turns and light moves with it. In a way, the shadow connects everything: physics, biology, history, and perception. It's how we came to understand motion, how we learned to measure, how we developed awareness of change. The alternation of light and dark gave us not just clocks, but consciousness of time itself. We learned that things move, that days pass, that life unfolds in sequence. The first clock wasn't just made of shadows. It made the idea of time real. When you watch a shadow now, on a sundial, a building, a field, you're seeing more than light blocked by an object. You're watching the planet's rotation made visible. The motion beneath your feet is revealed in the slow drift of darkness across the ground. That movement is continuous, unbroken, so regular that it can lull the mind, steady the breath, and remind you that time isn't rushing anywhere. It's moving exactly as it always has, exactly as it must. The Earth's rotation is the ultimate clock, vast, unhurried, consistent. Its accuracy is beyond anything we can build. Even as it slows by fractions of a second per century, its rhythm is truer than any mechanism. The shadows that sweep across its surface are the clock hands of a living world. When ancient builders aligned temples to the sunrise, when astronomers marked solstices with pillars of stone, they were not inventing timekeeping. They were listening to it. They were reading the clock made of shadows that has always been here, turning with the earth, keeping perfect rhythm with the movement of the sun. Every morning that clock resets itself, and every night it pauses in the darkness, waiting to begin again. You don't need instruments to see it. Just look at where light meets shade. Look at how it shifts, how it never stays still, how it slides across walls, across faces, across the ground. That's the Earth's heartbeat, turning beneath you, counting the passage of the day in the oldest way possible. The shadow tells you everything: where you are, what time it is, and how the world moves. And as the light fades, as the planet continues its turn into night, the shadow disappears not because time stops, but because you've entered the other half of the cycle. The clock doesn't end. It continues invisibly, turning in darkness until the sun returns. The Earth never stops spinning. The clock never stops ticking. The rhythm never falters. A clock made of shadows, simple, silent, eternal. It began long before we measured time, and it will go on long after timekeeping becomes unnecessary. It's the motion of the earth made visible, the memory of a light written on the ground, the quiet proof that the world is always turning. If you close your eyes right now, the world feels still. The floor beneath you doesn't move. The air doesn't rush past your face. The bed, the chair, the walls, they all seem fixed in place. You could stay there for hours, breathing quietly, without the faintest sensation that you are hurtling through space. Yet at this very moment, you are moving faster than the speed of sound. The ground beneath you is rotating eastward at hundreds of meters per second. The entire planet is orbiting the sun at nearly 30 kilometers per second. The sun itself is racing around the center of the Milky Way at more than 200 kilometers per second. Everything is in motion, and yet, to you, it feels like nothing at all. That illusion of stillness is one of the most comforting experiences we have, and one of the most deceptive. The reason we feel so steady, even on a spinning planet, is that everything around us moves in perfect harmony. The air, the oceans, the mountains, your own body, all are part of the same rotation. There's no relative movement between you and the surface of the Earth. No sudden change, no acceleration, no friction to detect. The motion is constant, and constancy feels like rest. Our bodies are not built to sense absolute motion. We can feel acceleration, the beginning or end of a change, but once movement becomes steady, the senses fall silent. That's why you can sit comfortably in an airplane cruising at 900 kilometers per hour and feel as though you're sitting in a chair in your living room. You only feel the plane move when it takes off, turns, or lands. when the rate of motion changes. The same principle applies to the Earth. Because the rotation is perfectly smooth and unchanging, it generates no signal for the body to notice. You move with the planet completely, so from your perspective, you are motionless. The physics behind this calm is simple, but profound. Newton's first law of motion, the law of inertia, states that an object in motion will remain in motion unless acted upon by an external force. You, the air and the earth beneath you are all part of one enormous rotating frame of reference. Inside that frame, everything shares the same velocity. There is no friction between you and the air around you, no drag pulling you backward. You're carried along with the surface at the same speed, so you feel nothing. Motion without acceleration becomes indistinguishable from rest. This shared motion is also what keeps the atmosphere stable. The air rotates with the planet bound by gravity. When the Earth turns, the atmosphere turns with it. If the planet spun while the air stayed still, you'd feel winds faster than hurricanes constantly sweeping across the surface. But gravity couples the air to the planet's rotation, creating a kind of invisible cocoon of motion. From the surface, everything moves together. Even the clouds, the wind, and the oceans follow this shared rhythm. They shift relative to one another, but not relative to the rotation itself. It's an elegant balance, a natural synchronization that turns potential chaos into calm. It's easy to take that balance for granted. When you stand outdoors and feel a breeze, you might imagine that's the atmosphere rushing over a stationary Earth. In reality, both you and the air are spinning together, and what you feel is only a tiny difference between their motions. The real speed, the speed of the planet's rotation beneath you, is hidden. At the equator, it's about 1,670 kilometers per hour. At mid-latitudes, it's less. Near the poles, it approaches zero. Yet no matter where you stand, it feels the same. The rotation doesn't push or pull, it simply carries you with it. This shared movement creates a sensation that has no direct equivalent in daily life. Motion so constant that it becomes indistinguishable from stillness. You are, in a literal sense, always in free fall toward the centre of the Earth, held in place by the balance between gravity and the centrifugal effect of rotation. The ground beneath you is pressing upward just enough to counteract the pull of gravity, but that balance doesn't feel like motion. It feels like stability. It's the same feeling astronauts experience in orbit, except that for them, the balance is perfect enough that they appear to float. You're experiencing the same principle, just from the inside of the system rather than the outside. That invisible steadiness is the reason life can exist so comfortably on a spinning world. If the Earth's rotation were irregular, if it sped up or slowed down dramatically, we would feel it as immense forces sweeping across the surface. The oceans would surge, the air would whip violently, and gravity itself would fluctuate. But the rotation is nearly perfect. The planet turns with astonishing regularity, varying only by milliseconds over long stretches of time. It's a precision greater than almost any machine humanity has ever built. And because of that precision, the world feels serene. It's interesting to consider that for most of human history, the feeling of stillness was proof that the Earth did not move. People looked at the sky and saw the sun rising and setting, the stars wheeling above them, and concluded that the heavens must be in motion while the ground remained fixed. It made sense. After all, if the Earth was spinning, wouldn't we feel it? Wouldn't birds be swept backward, or clouds ripped from the sky? It took centuries of observation and reasoning to overturn that intuition. The Polish astronomer Nicholas Copernicus, in the 16th century, was one of the first to propose that the apparent motion of the sun and stars was an illusion created by Earth's rotation. His insight contradicted common sense but aligned perfectly with physics. Constant motion creates stillness, not turbulence. When Galileo later defended the same idea, he pointed out that passengers in a smoothly sailing ship don't feel motion either, a perfect analogy for the spinning planet. Inside the ship, objects move as they would on land. A dropped ball falls straight down, not backward. The air doesn't rush to the rear. The laws of motion are the same in all frames moving at constant velocity. The only way to detect motion is to look outside, to see the shore receding, the stars shifting, the sun setting. That realization changed everything. The stillness we feel isn't evidence that the earth stands still. It's evidence that we're moving with it completely. Once people understood that, the illusion of stillness became something more profound, a reminder of how perfectly we belong to the planet's motion. Every structure we build, every step we take, every breath we draw, happens within a system that's rotating at immense speed. We don't notice it because we're part of it, because the atmosphere and the ground and our own bodies share the same movement. There's no boundary between the world's rotation and our experience of space. The stillness we feel is the harmony of motion, not the absence of it. There are moments, though, when the illusion flickers. Standing under a sky full of stars, you might see them rise slowly in the east and fall in the west. Watching that motion, the whole dome of night turning above you, is one of the few ways to perceive the Earth's rotation directly. The stars are not moving. You are. If you let yourself watch long enough, you can sense the turning of the world beneath your feet. It's subtle, almost meditative. The stillness becomes motion, and motion becomes stillness again. The two are inseparable, like light and shadow. The same realization comes at sunrise and sunset. The glow on the horizon isn't the sun moving toward you, it's you rotating toward it. The horizon is sweeping beneath your feet, carrying you into the light. But the experience is so smooth, so continuous, that the mind doesn't register motion, only change. You see colour shift, shadows stretch, the air warm, all consequences of rotation translated into sensory language. You feel the world turning, but not as movement. You feel it as time, that perception of time as motion. The sense that one moment flows into the next is another expression of the planet's rotation. The length of a day, the alternation of light and dark, the rhythm of waking and sleeping, all arise from the same 24-hour spin. The stillness we experience is not the negation of that spin, but its embodiment. Without the constancy of rotation, there would be no sense of calm at all. The planet's smooth, silent motion is the foundation of the peace we associate with stillness. It's remarkable to think how sensitive we are to even small deviations from that balance. When you're in a car that accelerates or slows, you feel it immediately. When an airplane turns slightly, your inner ear detects it. The Earth's rotation is so steady that it never triggers those senses. The vestibular system in your inner ear, which monitors balance and motion, responds only to changes in acceleration. On a turning planet, there are none. The spin is constant, unvarying, unnoticeable. The absence of that signal is what we interpret as stability. That stability defines our entire physical intuition. We learn to think of the ground as stationary, of the sky as moving, because that's what our senses tell us. The reality is the opposite, but the illusion is perfect. It's so complete that even after centuries of scientific proof, it still feels more natural to imagine the sun rising than the earth rotating. The stillness of the world is the most persistent illusion in human experience, sustained by the perfect synchronization of everything around us. But it's more than illusion, it's also truth in a way. Within our own frame of reference, the earth is still. Motion is always relative, and in the reference frame of the rotating planet, we're at rest. Physics allows both perspectives to be correct depending on the viewpoint. The paradox dissolves once you realize that motion and rest are not absolute conditions, but relationships between things. To you, the world feels motionless because, relative to you, it is. To an observer far away, the same world spins in space. Both are real. Both describe the same reality from different vantage points. That relativity of stillness and motion adds a kind of beauty to the experience of living on a spinning planet. You're always in motion, yet always at rest. The world turns beneath the stars, carrying you with it, and the calm you feel is the direct result of that motion. The silence you experience isn't emptiness, it's the soundless perfection of a balanced system in constant movement. Even in the most literal sense, the Earth's spin creates sensations we associate with calm. The constant rotation smooths out variations in temperature between day and night, distributes sunlight across the globe, and drives the cycles of atmosphere and ocean that sustain life. The stability of climate, the regularity of weather, the predictability of dawn and dusk, all come from that rotation. The stillness we find in nature, in a quiet morning or a gentle evening, exists because the world is turning steadily beneath us. Motion creates balance. Balance creates peace. If you could somehow stop the Earth's rotation for a moment, the illusion of stillness would vanish instantly. The air would continue moving at its previous speed, creating winds of unimaginable violence. The oceans would surge across continents. The very ground would convulse under the change in inertia. It's the rotation that prevents those things. The smooth, continuous motion that keeps the surface, the air, and everything on it in perfect agreement. The stillness we feel isn't fragile. It's the strongest possible form of stability, the kind created by balance in motion. Astronauts sometimes describe a similar paradox. In orbit, they travel at over 27,000 kilometers per hour, circling the Earth every 90 minutes, yet they report feeling absolute stillness. Floating in microgravity, with no friction or air resistance, they experience the same sensation we do on the surface: motion without change, speed without awareness. They can look out the window and see the Earth moving beneath them, yet inside the spacecraft, everything is calm. It's the same principle extended to a different scale. Stillness isn't the absence of motion, it's the absence of disturbance. That realization that calm and movement can coexist reshapes how we think about the world. It means stability isn't static, it's dynamic. The quiet you feel when you sit outside and listen to the wind, the sense of peace that comes with watching clouds drift, all are parts of a planet in motion, a balance so perfect it disappears into experience. The stillness is real, but it's made of motion. If you've ever watched a spinning top, you might notice that it seems most stable when it's spinning fastest. As it slows, it begins to wobble, then fall. The faster it turns, the more its motion keeps it upright. The Earth behaves the same way. Its spin gives it gyroscopic stability, holding its axis steady against the tugs of the moon and the sun. If the rotation ever stopped, the planet's orientation would drift chaotically, its seasons and climates destabilizing. The spin that we never feel is what keeps everything aligned. The sense of stillness we experience depends on the persistence of motion. It's a curious truth that the things we find most peaceful, the steady rhythm of waves, the slow rotation of the night sky, the predictable arc of sunrise, all come from motion too regular to perceive directly. The calm we associate with stillness is actually the serenity of perfect continuity. It's not that nothing is moving, it's that everything is moving together. So when you feel the quiet of the world, when you sense the air at rest and the ground beneath you unmoving, remember what that stillness really is. It's the harmony of rotation, the equilibrium of a spinning planet carrying you smoothly through space. The reason you don't feel the motion is the same reason life can exist within it. The Earth's turning is not a background to stillness. It is stillness, translated into motion too perfect to feel. The next time you stand outside at night and feel the calm of the air around you, you can think of what's really happening. The world beneath you is turning eastward, the stars are sliding overhead, and the moon is tugging gently at the seas, yet everything feels steady, quiet, balanced. The sense of stillness you feel isn't an illusion to correct. It's the lived experience of a world in perfect motion. A reminder that peace doesn't mean things aren't moving. It means they're moving together, without friction, without change, without interruption. When night falls, the sky begins to move. The stars appear to drift from east to west, slow and smooth, as though the entire universe is turning above you. If you stay outside long enough, you'll see constellations slide toward the horizon and new ones rise to take their place. The moon moves through its steady path, and the planets, brighter and steadier than the stars, shift night by night across the backdrop of the constellations. It looks like everything beyond the Earth is in motion, but the truth is reversed. The sky isn't spinning around you. You are the one turning beneath it. The spinning of the Earth gives the heavens their apparent motion. Every night, as the planet rotates once on its axis, we sweep through the star's field of light, creating the illusion that the entire sky is revolving around us. The same spin that brings sunrise and sunset also makes the stars rise and set. It's one motion seen from two different sides, daylight revealing one half of the sky, night revealing the other. The stars are fixed in space, but because we're standing on a moving surface, they seem to move in vast circles across the darkness. If you could watch the whole night sky at once, you'd see a remarkable pattern. Around one point near the North Pole, all the stars appear to rotate. Some circle high above, others skim the horizon, but all trace arcs centered on that same invisible spot. In the Northern Hemisphere, that point lies very close to Polaris, the North Star. Stand beneath it, and you'll see it remain almost perfectly still as the rest of the sky wheels around it. That's because Polaris lies almost directly above the Earth's axis of rotation, the line the planet spins on. The North Pole points toward it, and as the Earth turns, that axis stays fixed relative to the background of space. To you, it looks as if the stars are turning around a motionless beacon, but really, it's your own planet spinning on its tilted axis. If you travel south, that illusion changes. The North Star sinks lower on the horizon until, at the equator, it disappears completely. There, the stars rise straight up in the east and fall straight down in the west, drawing perfect lines across the sky. Farther south still, in places like Australia or South America, the stars seem to rotate around a different point, the southern celestial pole, which has no bright guiding star. To stand there and look up is to watch the sky spin in reverse, opposite to the motion seen in the north. The pattern flips, but the cause is the same, the rotation of the Earth. People noticed these motions long before they understood them. To the earliest observers, the sky's turning was the most reliable thing in existence. Every night the same stars appeared, the same constellations followed one another, the same celestial patterns repeated with perfect regularity. It was natural to imagine the heavens as a great sphere surrounding the Earth, a cosmic dome that turned once each day. The stars were thought to be fixed to that dome, carried by its rotation. The sun, moon, and planets were believed to move along their own paths within it, slower and more complex, but still part of the same rotating cosmos. It was an elegant model for a long time, simple, accurate to the eye, and deeply human in its perspective. For countless generations, this view of the turning sky shaped how people lived and thought. The apparent motion of the stars gave direction and time. Sailors navigated by them, farmers planted by them. Priests and astronomers built calendars from their rising and setting. Each star became part of a larger clock. When certain constellations appeared at dawn, it meant a season was beginning. When others disappeared into the glow of sunset, it meant another was ending. The rotation of the Earth, though no one yet called it that, was already the foundation of human timekeeping. What's extraordinary is how accurately ancient observers recorded these patterns. Long before telescopes or clocks, people could predict celestial events with remarkable precision. They watched the positions of stars along the horizon, noting where each one rose and set. They noticed that the whole sky seemed to shift slightly over generations, a result of the slow wobble of the Earth's axis, though they couldn't have known that then. They aligned temples, monuments, and cities to the stars' paths, embedding the motion of the heavens into stone. In every culture, the spinning sky was both a mystery and a measure of order. If you go far enough away from city lights and look up, you can see the same movement those early watchers saw. The longer you stay still, the clearer it becomes. The stars slide at a rate of 15 degrees per hour, one complete rotation in 24 hours. But your eyes aren't fast enough to notice that speed directly. The motion is too slow, too smooth. Only when you compare the sky across hours, or capture it with a camera, does it reveal its sweep. In long exposure photographs, the stars draw perfect circles, arcs of light around the celestial poles. Those circles are the record of the Earth's rotation. Each one is a trace of the planet's motion, written in light across the darkness. Even in cities where few stars are visible, the same motion continues overhead. The moon, brighter than all but the sun, follows a slower version of the same path, rising and setting each night as the Earth turns. Planets do the same, though their orbits around the sun make them wander slightly against the background stars. To the naked eye, they move with the same grand sweep, east to west, across the sky, carried by the turning of the world. If you think about it carefully, the sense of movement you perceive in the stars is almost the opposite of what's really happening. The stars appear to move westward, but the Earth rotates eastward. You can test this yourself by watching the sun rise. It appears in the east because that's the direction the Earth is turning toward the light. You rotate into the day. When you watch the stars sink in the west, you're rotating away from them. The sky's motion is the mirror image of your own. The universe seems to move around you, but in reality you're the one spinning, and the cosmos is standing still. Understanding that reversal was one of the greatest intellectual shifts in human history. When astronomers like Copernicus and later Galileo proposed that the Earth turned instead of the heavens, they were not only correcting a scientific error, they were changing humanity's relationship to the sky. The stillness we once believed in was replaced with movement, and the movement we saw was recognized as illusion. Yet that illusion remains powerful. Even today, when we know the physics, we still see the stars as moving. The Earth's spin is something you understand with your mind, not something you ever truly feel. There's something beautiful in that paradox, that you can watch the whole universe seem to rotate and know it's really your own world doing the turning. It gives a sense of connection between what's visible and what's invisible, between perception and reality. The stars, which seem eternal, are actually markers of our motion, reflections of the planet's spin projected across the heavens. Every night, that motion repeats. The constellations make their steady circuit, rising and setting in the same order. But because the Earth also travels around the sun, the timing shifts slightly each day. The stars rise about 4 minutes earlier every night, completing a full extra cycle over the course of a year. That's why the stars you see in the summer sky are different from those you see in winter. The planet's orbit around the sun adds another layer of motion to the turning sky, combining daily rotation with yearly revolution. What you see above you at any moment is a pattern created by both, a celestial choreography involving time, light, and perspective. If you were to watch the sky for a full year from the same place, you'd see the constellations slide slowly from east to west with the seasons, then return to their starting points. Each star has its season, its time to shine in the night, and its time to vanish into the sun's light. Over millennia, even those seasons change as the axis wobbles, shifting the celestial poles and altering which stars dominate each era. The entire sky, though vast and ancient, is part of the same dance, the slow, steady spinning of the Earth beneath the stars. For most people, that motion is background, unnoticed, like breathing. But for those who study or navigate by the sky, It's as familiar as sunrise. Astronomers use the rotation to track time with exquisite precision. A sidereal day, the time it takes for the Earth to complete one rotation relative to the stars, is about 4 minutes shorter than the solar day we use for our clocks. That difference arises because, as the Earth spins, it also moves slightly along its orbit around the Sun. It has to rotate a little more than 360 degrees each day to bring the Sun back to the same position in the sky. The stars, being far away and unmoving relative to that orbit, rise earlier. The Earth's spin and orbit combine to define the cycles of night and day, year and season, astronomy and time. That connection between the spinning Earth and the spinning sky is more than geometry. It's the source of our sense of rhythm, of the passage of time. The alternation of stars, the slow rotation of constellations, the predictable return of the same patterns, all of it tells us that the universe has continuity. The turning sky is the most ancient clock of all, vast and silent, ticking once every rotation of the world. If you look long enough, you can start to feel that clock moving. The stars near the horizon rise and fall faster, tracing longer arcs. Those near the pole creep slowly, circling endlessly without ever setting. In the southern sky, if you're far enough south, you can see a faint ring of stars around the point where the planet's axis extends into space. At that centre there is no movement at all. It's the one still point in a sky made of motion, not because it doesn't move, but because it lies directly along the axis of rotation. It's like the spindle of a wheel, motionless at the centre while everything else turns around it. If you could stand on the surface of the Earth at night and see with perfect clarity, you would notice even more subtle motions layered into the stars' apparent paths. The Moon, moving in its orbit, shifts slightly eastward each night. The planets wander against the background stars, sometimes appearing to move backward, a phenomenon called retrograde motion, as the Earth overtakes them in its orbit. All of these motions combine into a living dynamic tapestry. But the largest and most consistent of them all is the one created by the Earth's rotation, the steady, unwavering turning of the entire sky around invisible poles. This apparent motion has guided human orientation for as long as there have been people to look up. The North Star has long been a symbol of direction and stability. Travellers and sailors used it to find their way through darkness and open sea, measuring their latitude by its height above the horizon. When you stand in the northern hemisphere and look at Polaris, its angle above the horizon equals your distance north of the equator. That relationship is no coincidence. It's geometry, the direct consequence of living on a spinning sphere. The sky, in that sense, is a map of the Earth's rotation, projected outward. Every coordinate in the heavens corresponds to one on the globe. Even now, in an age of satellites and GPS, that relationship remains constant. The Earth still spins beneath the stars, and the stars still rise and set as they always have. The sky's motion connects every generation across time. The same stars that circled above ancient civilizations circle above you now, shifted only slightly by the slow precession of the axis. The same rotation that gave them their seasons and calendars continues, steady and silent. When you step outside at night and let your eyes adjust to the darkness, you can feel that connection. The faint glow of starlight is ancient, the patterns familiar, the motion continuous. You're standing on a planet turning through space, watching the projection of that rotation across the sky. The star's slow drift is not a sign of movement above you, but a reflection of movement within you, your own motion as part of a rotating world. It's easy to forget that the sky you see is always changing, even while it appears eternal. The same constellations that mark your nights are shifting ever so slightly each second. The illusion of permanence is created by speed too vast and uniform to notice. The Earth spins, and the stars appear to move. The spin never stops, the motion never falters, and the stillness you feel beneath it is the balance that makes it all possible. The next time you find yourself outside after dark, try standing still for a while and simply watching the sky. Choose a bright star and see how it drifts relative to a nearby tree, roofline, or mountain. It may take time, but eventually you'll notice the shift, the quiet glide of the heavens. In that moment, you'll be seeing the planet's rotation made visible, the same turning that gives you morning and evening, time and rhythm, night and day. The spinning sky is not a backdrop. It's a mirror. It shows you the motion you're part of, the rotation that defines every day of your life. The stars are not circling you. You're moving with the Earth, watching the universe turn from your shared place within it. Every revolution of the sky is a reminder that motion and stillness are the same thing seen from different sides. The Earth turns, and the heavens seem to move. The illusion is perfect, the rhythm eternal, and the beauty of it lies in the balance between what is real and what is seen. The spinning sky is the quiet proof that the world beneath you is never at rest, and that in its motion, everything you know finds order, rhythm, and peace. It's hard to imagine the Earth not turning. The motion is so constant, so gentle, that it feels like the background condition of existence itself. Day follows night, night follows day, and the sequence feels eternal. The spin of the planet has been the same for billions of years, setting the rhythm for oceans, air, and life. But suppose for a moment that it stopped. Not forever, perhaps, but suddenly, or even gradually. What would that mean for the world we live in? What would stillness feel like on a planet that has never known it? If the Earth were to stop spinning instantaneously, the consequences would unfold not as noise, but as violence written into physics. The surface of the planet is moving fastest at the equator, about 1,070 kilometers per hour eastward. Everything attached to the ground, the oceans, the air, even you, is moving at that same speed. If the rotation stopped in an instant, inertia would keep everything moving. The atmosphere would rush forward at more than 1,000 kilometers an hour. The oceans would surge, rising up and sweeping across continents. It wouldn't be wind, as we know it, but a planetary-scale hurricane, a flood of air and water continuing in motion while the ground beneath it ceased to turn. It's not something that could ever happen naturally. There's no force in the solar system capable of halting a spinning planet so suddenly. The energy required would be unimaginable, enough to vaporize the crust and boil the oceans. Yet even as a thought experiment, it reveals something profound about the nature of motion. The reason everything seems calm now is not because the Earth is still, but because everything moves together. The rotation is perfectly shared. It's balance in motion. The chaos would come only if that balance were broken. But suppose the Earth didn't stop instantly. Suppose instead that its rotation slowed gradually, over thousands or millions of years. That's not impossible. It's happening already, at a nearly imperceptible rate. Tidal friction from the moon is lengthening our days by milliseconds per century. Over eons, the slowing could continue until the Earth rotated so slowly that one side always faced the sun, just as the moon always shows one face to us. That scenario, while far beyond any human timescale, offers another vision of what stopping would mean. A world where half the planet is in eternal day and the other half in perpetual night. If that were to happen, the transformation would be slow but relentless. As the rotation slowed, days would lengthen, nights would grow longer, and the rhythm of temperature would become extreme. On a 48-hour day, the side facing the sun would bake under continuous light, while the dark side cooled and froze. Winds would strengthen as heat flowed from one hemisphere to the other, creating powerful global storms. Oceans would begin to migrate toward the poles and the equator differently than they do now, responding to changes in centrifugal force. That force, the outward push from the planet's spin, is what makes the Earth slightly flattened at the poles and bulged at the equator. It's also what causes water to pile up more thickly around the equator than near the poles. If the Earth stopped rotating, that bulge would relax. The oceans would flow toward the poles, flooding high latitudes and exposing equatorial regions. Vast new lands would emerge, while areas now under ice might lie beneath water. It would be a complete reshaping of geography, guided not by tectonics or erosion, but by the redistribution of mass when motion ceased. The atmosphere would undergo its own transformation. Right now, the rotation of the Earth gives rise to the Coriolis effect, a subtle deflection that shapes global winds and ocean currents. It's what makes hurricanes spin, what drives trade winds, and what stabilizes weather patterns. If the planet stopped, the Coriolis effect would vanish. Air would flow directly from hot to cold regions, from the eternal day side to the night side in a constant violent circulation. Over time, those winds might balance into a steady flow, a permanent global breeze, but the transition would be chaotic. The line between the bright and dark hemispheres, the terminator, would be a region of perpetual twilight. That thin band circling the planet might become the most habitable zone. On one side, the sun would never set. On the other, it would never rise. In the middle, eternal dawn and dusk with moderate temperatures might offer a narrow refuge for life. The ecosystems of such a world would be unrecognizable. Plants would have to adapt to endless light or endless dark. Animals would evolve for stability rather than rhythm. Circadian cycles tuned for rotation would lose their meaning. If the stopping were gradual enough, life might adjust. Evolution has already proven resilient to immense change. Ice ages, asteroid impacts, shifts in atmosphere and temperature. A slowly halting Earth would present new challenges, but not necessarily extinction. Species might migrate toward the twilight band, adapting to constant conditions rather than alternating cycles. The photosynthetic balance between day and night, light absorption and rest, would have to evolve in new directions. The concept of day would fade from meaning, replaced by geography, the bright side, the dark side, and the edge between them. The sense of time itself would dissolve in such a world. Humans, if they still existed, would no longer measure hours by the movement of the sun. The sky would be static for half the planet and perpetually starless for the other half. Only the slow orbit around the sun would bring change, a year defined not by rotation but by revolution. The sun's position might shift slightly over that time, creating long, slow seasons, but the daily rhythm that once structured life would be gone. Time would lose its familiar pulse. The consequences would reach even deeper into the planet's systems. The molten outer core of the Earth, where the magnetic field is generated, depends in part on the planet's rotation to maintain its convective flow. A slowing rotation might weaken that magnetic field, exposing the surface to higher levels of cosmic and solar radiation. The auroras would fade. The invisible shield that protects life from charged particles would falter. Over long timescales, the atmosphere itself might erode more quickly under the assault of solar wind as it has on Mars, another reminder that motion isn't just background but protection. Even gravity would feel different in subtle ways. Right now, the centrifugal force from rotation slightly counteracts gravity at the equator, making you weigh a fraction of a percent less than you would at the poles. If the Earth stopped, that difference would vanish. The equator would feel heavier, though only by a small amount, about a 0.5% increase. It's minor, but noticeable in principle. You'd feel the world hold you just a little tighter, as though it had taken back the tiny sliver of freedom rotation provides. But perhaps the most profound change wouldn't be physical at all. It would be psychological. The rotation of the Earth defines the human sense of rhythm, of passing time, of continuity. The alternation of day and night shapes how we think, rest, and dream. Without it, our internal clocks would lose their anchor. The concept of sleep might change completely. On the bright side, people would have to live in cycles disconnected from sunlight. On the dark side, artificial illumination would replace the sun entirely. Society would fragment along lines of light and shadow. The idea of morning and evening, one of the oldest and most universal experiences, would disappear. For early humanity, the rising and setting of the sun were proof that the world was alive. The daily cycle was the first thing we trusted, the first pattern that gave structure to our understanding of time. A motionless Earth would be a silent one, stripped of that ancient rhythm. The sky would no longer move, the stars would no longer rise or set. Constellations would hang frozen above the dark hemisphere forever. The sun, motionless overhead, would carve the same shadows eternally on the bright side. The beauty of the world, which comes from change, would flatten into permanence. That permanence would not mean peace. The bright side would grow scorching hot. Without rotation to distribute heat, temperatures would rise beyond the limits of most life. The air might boil near the subsolar point, the spot directly beneath the sun, creating a vast desert-like region where nothing could survive. On the dark side, the cold would deepen until the atmosphere itself condensed into frost. Carbon dioxide, oxygen, and nitrogen could freeze on the ground, forming chemical snows. The air would migrate toward the cold hemisphere, thinning the atmosphere on the bright side and thickening it on the dark. The planet's balance would become self-reinforcing, cold begetting colder, heat feeding heat. Over geologic time, the Earth might stabilize in that configuration, half scorched and half frozen, with a band of temperate twilight dividing them. The oceans would settle into new basins. Mountain ranges would erode differently under unending light or shadow. Weather would exist only as circulation between extremes. The planet would remain dynamic, but its motion would be internal, convection, tectonics, tides driven by the moon, rather than rotational. The outer rhythm would be gone, replaced by slower cycles measured in centuries and millennia. In that distant, frozen world, the moon would still circle above, though perhaps differently. The same tidal forces that once slowed the Earth's spin would eventually bring the system into equilibrium, with the moon locked overhead above one hemisphere. The same face of the Earth would always face the same face of the moon. The two bodies would orbit in perfect synchrony, their rotation and revolution aligned. To an observer on the bright side, the moon might hang eternally in one position in the sky, changing only in phase as sunlight hit it from different angles. To those on the dark side, the moon might never rise at all. The faint blue line of atmosphere glowing at the edge of the planet would still mark the boundary between Earth and space, but it would be thinner, colder, less alive. The Earth would have become quiet, not in a peaceful way, but in a literal one. The spinning air that once roared as wind would have stilled into a permanent pattern. The tides would have slowed to a crawl. Even earthquakes might become less frequent as the planet's shape adjusted to its new equilibrium. The Earth would not die. It would simply change its tempo from rhythm to stillness, from rotation to pause. In truth, the Earth can never stop completely. The laws of physics forbid it from reaching absolute rest. Every planet in the universe spins, because angular momentum once given is conserved. Collisions may slow it, friction may shape it, but only eternity itself could truly stop motion. Even the gradual slowing from tidal friction will take longer than the sun's lifespan. Long before the Earth could ever stop turning, the sun will expand into a red giant, engulfing the inner planets and erasing the stage on which this quiet dance takes place. The spin will outlast everything else we know. Thinking about that makes the present motion feel different. The rotation we live within, the gentle, perfect turn that brings day and night, is not guaranteed, but it's durable. It's a state of balance, billions of years in the making. It gives the world its weather, its tides, its stability, and its time. It is the foundation of everything familiar. The thought of it stopping is not just a physical scenario, but an existential one. A reminder that what feels still is actually fragile, sustained by motion we rarely notice. If the Earth ever stopped, even for a moment, the consequences would reach everywhere, through the air, the sea, the sky, and the mind. The illusion of stillness we rely on would shatter, replaced by the true scale of motion that's always been hidden. But the truth is that stillness we imagine is impossible. The world can't be motionless. It was born spinning, and it will spin until it ceases to be a world at all. And perhaps that's what makes its current motion so precious. Every sunrise, every turning of the stars, every rhythm of light and shadow is a sign that the planet still moves, still keeps its balance, still turns beneath our feet. The Earth's spin is the quiet force that makes life possible, invisible yet absolute. If you ever find yourself wondering what it would be like if the Earth stopped, consider this. The feeling you have right now of calm, of balance, of the world steady beneath you, is already what that stopping would destroy. The stillness you experience isn't the absence of motion, it's the perfection of it. The Earth is not meant to stop. Its beauty lies in the fact that it keeps turning endlessly, silently, carrying us with it through time and space. Every moment you've ever lived has unfolded on a turning world. Every breath, every thought, every quiet second of sleep has taken place on a sphere that has never stopped moving. It's been spinning since the first fragments of dust came together to form the Earth, and it will continue long after everything familiar is gone. The rotation has changed, yes, slowed, tilted, adjusted, but it has never ceased. It is one of the most enduring motions in the universe, a slow, unbroken rhythm that began before life and will outlast it. When the Earth first formed from the debris of the early solar system, it spun faster than it does now. The newborn planet was hot, molten, chaotic. Collisions were constant. Each impact transferred energy and momentum, and the young Earth's rotation fluctuated wildly until it found a kind of balance. In those early days, a single rotation may have taken only a few hours. The day was short, the sun rose and set swiftly, and the world's surface glowed with the energy of its own creation. Over billions of years, as the planet cooled, and the moon's tides pulled against its spin, that rotation lengthened into the 24-hour cycle we know now. But the turning never stopped. It simply evolved, smoothing into the steady pace that defines the rhythm of time. That motion has persisted through every era since. The continents have drifted, oceans have opened and closed, species have risen and vanished, but the planet's spin has continued without interruption. It is the one constant through all the Earth's transformations. When the first microbial life appeared in the oceans, the planet was already turning. When forests grew, when dinosaurs walked, when ice ages advanced and retreated, the world kept rotating under the same gravitational laws that guided its birth. The same spin that began in that violent beginning still moves you now. Every dawn, every falling night, every star crossing overhead is the latest turn of an ancient wheel. That wheel is as close to eternal as anything we know. The energy that keeps the Earth rotating is vast, the product of its mass, and the angular momentum it inherited from the spinning cloud of gas and dust that became the solar system. According to the laws of physics, that momentum can't vanish on its own. It can only be transferred, and the only significant exchange in this case is with the moon. The tides act as a brake, drawing a minute amount of energy from the Earth's spin and giving it to the moon's orbit. The result is the slow lengthening of days and the moon's gradual drift outward. Over billions of years, this exchange has only slowed the Earth's rotation by a fraction. The rhythm has endured almost unchanged, its tempo softening so gently that no living being could ever notice it. To imagine the persistence of that motion is to confront the scale of time itself. The human sense of duration, minutes, hours, years, is nothing compared to the age of the planet. The Earth has completed roughly 1.6 trillion rotations since it formed. Each turn has been unique, shaped by the shifting weight of oceans, the drag of winds, the pull of the moon, yet all have been part of the same continuum. There has never been a moment when the Earth stood still. Even as it slows, the rotation continues, endless in practical terms. If you could somehow watch the entire history of the planet unfold at high speed, you would see it spin like a glowing ember cooling in space. The continents would slide and collide, mountains would rise and erode, ice would spread and melt, and through it all, the planet would keep turning. The rhythm would change almost imperceptibly. the days lengthening as the moon drifted outward, the tilt of the axis oscillating slightly, the tides weakening, but the rotation would never end. It would look like breathing stretched across eons, the slow, steady pulse of a living world. That rotation has shaped every aspect of the planet's identity. The division of light and dark, the flow of air and water, the stability of climate, the very definition of time, all arise from it. The Earth's magnetic field, generated by the churning of its molten core, is influenced by the spin. The weather systems that distribute heat and moisture depend on it. The habits of every organism, from bacteria to humans, are synchronized to its cycle. The rotation is not just motion. It's the framework within which all life exists. It is the measure that every living thing carries within itself. When you wake in the morning, you're responding to a rotation that began long before your species existed. Your circadian rhythm, the internal clock that governs sleep and wakefulness, is a biological echo of the planet's spin. Every plant that opens to sunlight, every bird that migrates by season, every tide that rises and falls, all are expressions of that ancient motion. It is written into the chemistry of life. The Earth's spin is not just a background condition. It is part of what life is. Even the stars you see at night are visible only because of that rotation. The entire dome of the sky turns because the planet turns. The constellations wheel around the poles, the sun rises and sets, the moon glides across its path, all because the Earth continues to move. The illusion of the sky's motion is one of the clearest ways to witness the rotation made visible. Each night, you can see the proof of it in the slow drift of light across darkness. Without that turning, there would be no night sky as we know it, no alternation of light and dark, no rhythm to mark the passage of time. The persistence of the rotation is also a form of stability. It acts like a gyroscope, holding the planet's orientation steady as it moves through space. Without that stability, the axis might tilt erratically, producing catastrophic shifts in climate. The steady spin keeps the planet upright, maintaining its seasons and its habitability. The tilt oscillates slightly over tens of thousands of years, but the rotation itself provides the foundation that prevents chaos. The Earth's ability to support life depends on that constancy. The eternal motion brings not disorder, but balance. If you were to compare the rotation of the Earth to that of other planets, you'd find a pattern written into the whole solar system. Every planet spins, some faster, some slower. Jupiter, immense and gaseous, rotates once every 10 hours, its equator moving faster than a bullet. Venus turns so slowly that one day lasts longer than its year. Mars spins at nearly the same rate as Earth. All of them inherited their rotation from the same primordial disk of dust and gas, shaped by collisions and gravitational forces. The Earth's particular speed, one rotation in roughly 24 hours, is an accident of formation, but it's an accident that suits life perfectly. It gives us a balance of temperature and light, a cycle of activity and rest. Too fast and winds would rage across the surface. Too slow and heat would build and freeze in extremes. The Earth's rotation is not just continuous, it's ideal. That balance, though changing, is resilient. Even as the spin slows over eons, the change is so gradual that it maintains stability. The day lengthens by only a few milliseconds per century. In the time it takes for a mountain to erode, the Earth's day might lengthen by a single minute. In the time it takes for a continent to drift across an ocean, it might gain an hour. The timescale of that change is beyond comprehension. It's slow enough to be eternal in any human sense. If you imagine standing somewhere on the Earth's surface and feeling that spin directly, you would find it imperceptible. The velocity is immense, but because it's constant, it's invisible to the senses, yet its influence is everywhere. The equatorial bulge, the shape of the oceans, the pattern of winds and currents, the direction of storms, all are evidence of the rotation's power. Even gravity as you experience it is slightly altered by it. The centrifugal force of the spin counteracts a small fraction of the pull of gravity. making the planet's weight distribution even and its surface livable. Without rotation, gravity would feel heavier, and the Earth would be rounder, not the slightly flattened sphere we inhabit. There's something remarkable in the idea that such vast movement feels like stillness. The rotation happens quietly, so smooth that it produces no sensation. You move with it completely, part of the same motion, inseparable from it. Every point on the surface is engaged in that motion, carrying oceans, forests, and cities through space. The stars shift because you're turning beneath them, but your body feels nothing. The eternal rotation hides in plain sight, transforming motion into stability. From a distance, the Earth's spin is one of its most beautiful features. Photographs taken from space show the clouds, swirling in patterns shaped by rotation, storms curling into spirals, the blue arc of atmosphere glowing along the edge of the planet. Time-lapse images reveal the entire face of the Earth turning slowly, continents sliding into shadow and emerging into light. It looks alive, not just because of the life on its surface, but because of the motion itself. The rotation gives it character, a heartbeat visible from the void. Even the concept of forever changes when you think about that motion. The rotation is not infinite, but its continuation stretches beyond any scale of time we can hold in the mind. Long after human civilization is gone, the Earth will still turn. Long after the continents merge again into a single mass, it will still turn. Long after the oceans evaporate under a brightening sun, it will still turn, slower perhaps, but steady. The day will continue to lengthen until it matches the moon's orbit, when the two will become tidally locked. At that point, billions of years from now, one side of the Earth will always face the moon. Even then, the Earth will not truly have stopped. It will still be rotating once per orbit, still turning relative to the sun. The rotation will have evolved, not ended. In that distant future, the sun itself will change. It will expand, warming the Earth beyond habitability. Oceans will boil, the atmosphere will escape, and the surface will become barren. Yet even as that happens, the planet will keep turning. When the sun becomes a white dwarf, and the remnants of the solar system drift into darkness, the Earth's spin may persist, slowed, but not erased. The momentum it carries will continue, fading only over timescales so immense they defy meaning. The eternal rotation is not eternal in the literal sense, nothing is. But in every way that matters, it endures beyond everything we know. Thinking of that endurance can change the way you experience time. Every day you live is one more rotation of the planet. Every morning is the return of the same side to the sun. You measure your life in years, but years are only the count of rotations around a star. The days themselves are the deeper rhythm, the heartbeat that connects you to the first day and the last. You are part of that pattern, not an observer of it, but a participant. The turning of the Earth is the turning of your world, and you move within it effortlessly. The eternal rotation is what makes continuity possible. It's the reason we can predict sunrise, the reason we can sleep and wake, the reason the concept of time has meaning at all. Every mechanism we use to track moments, clocks, calendars, heartbeats, orbits, is an imitation of that primal motion. The rotation is the original measure, the baseline against which everything else moves. It's so consistent that it defines stability itself. The planet's spin is the physical expression of reliability, the ultimate repetition that underlies every change. If you stand still long enough under the night sky, you can feel that reliability. The stars drift so slowly that they seem eternal. The air is calm, the ground feels solid, and yet, beneath that stillness, the Earth is spinning, carrying you, the air, the oceans, and everything you know through space at immense speed. The stillness you feel is the harmony of that motion, the balance of forces so perfect that it becomes invisible. The eternal rotation isn't something you can sense directly. It's something you live inside of. It's the invisible rhythm that makes stillness possible. That rotation links you to everything that has ever existed on this planet. Every tree that ever grew, every creature that ever lived, every wave that ever broke on a shore, all moved with it. The same spin that lifts the sun above the horizon lifted it for every being that came before you. The same motion that carries your night sky carried the skies of the ancient world, the same stars tracing their circles through history. The rotation makes the passage of time tangible, binding past and present into a single, continuous movement. Somewhere, right now, the world is turning into morning. Somewhere else, it's turning into night. The line between them, the moving boundary of light and shadow, sweeps across oceans and continents, never stopping. That movement is the visible edge of eternity, the direct expression of the planet's rotation. It has been moving across the surface of the Earth for more than 4 billion years. It will continue to move long after every trace of human memory has faded. It's a motion that never grows old, never loses rhythm, never ceases to connect every moment to every other. If you could listen closely enough, not with ears but with awareness, you might hear it, not as sound but as presence. The world turning softly through space, the air and water keeping pace, the continents drifting with it. Every second, the planet completes another fraction of its endless circle, carrying everything it holds through the quiet of the universe. It's the one motion that never needs renewal, the one rhythm that never stops. The eternal rotation isn't a miracle, it's the simplest outcome of the laws of motion. But in its simplicity lies beauty. It's what allows change to exist within continuity, and life to exist within time. It's the movement that gives rise to all others. The rotation of a world that began in chaos, found balance and kept turning. Every day, it renews itself. Every night, it continues unseen. It has always been this way, and for as long as there is a world to turn, it always will be. The Earth doesn't only turn, it also travels. While the rotation spins us through day and night, another, even larger motion carries us through the deep quiet of space. The Earth moves in its orbit around the Sun, tracing a long, almost perfect ellipse, completing one circuit every year. Together, these two motions, rotation and revolution, define everything we understand about time, light, and life. One gives us the rhythm of a single day, the other the rhythm of the seasons. One turns us toward and away from the sun, the other carries us around it. They happen at once, layered and synchronized, so perfectly balanced that we never feel either. The Earth's orbit is immense, a circle more than 900 million kilometers around. The planet travels that path at an average speed of about 30 kilometers per second, fast enough to cross the diameter of the Earth in just 7 minutes. Yet from where you stand, there's no sensation of motion. The ground is still, the air is calm. The sun seems fixed in the sky, rising and setting in its predictable rhythm. But all the while, you're hurtling through space, carried by a planet that spins as it travels. The rotation and the orbit combine into a dance so perfectly smooth that it feels like rest. If you could step outside this motion and look back at the solar system from afar, you'd see the Earth tracing its graceful loop around the Sun, its axis tilted just enough to create the pattern of seasons. You'd see the Moon circling the Earth, the pair of them moving together through the same orbit. You'd see other planets following their own paths, each tilted, each spinning at its own pace. From that distance, the complexity would appear as harmony, a system of perpetual motion held together by gravity, moving not in chaos but in order. The orbit isn't a perfect circle, though it's close. It's slightly elliptical, meaning that the distance between Earth and Sun changes through the year. The difference is small, about 5 million kilometers, but enough to shift the intensity of sunlight a little. Ironically, the Earth is actually closest to the Sun in early January and farthest in early July, the opposite of what many people imagine. The reason the Northern Hemisphere experiences winter in January isn't distance but tilt. The axis of rotation leans about 23.5 degrees relative to the plane of the orbit, so that as the Earth travels around the Sun, each hemisphere alternately tilts toward and away from the light. That simple tilt, combined with the planet's steady spin, creates the seasons: the long days of summer, the short days of winter, the slow transitions in between. That relationship between tilt, spin, and orbit is one of the most delicate balances in nature. The rotation alone would give us days and nights, but without the tilt there would be no seasons, no cycle of change. The orbit alone would carry us through space, but without rotation, one side of the planet would burn while the other froze. Together, they create the rhythm of warmth and cold, light and dark, rest and renewal. The spin gives time its pulse, the orbit gives it its scale. Every day, the Earth turns once on its axis while travelling millions of kilometres along its orbit. The Sun rises and sets because of rotation, but it appears to return to the same place in the sky because of orbit. It takes slightly more than one full spin, about 361 degrees of rotation, for the Sun to appear in the same position overhead again. That extra degree corresponds to the fraction of the orbit completed each day. This is why the solar day, the one we live by, is about 4 minutes longer than the sidereal day, the true rotation period relative to the stars. The difference is small, but it connects our sense of time to the geometry of motion, a quiet reminder that every sunrise contains a trace of both rotation and revolution. The combination of these motions creates a world that is never truly repeating itself. No 2 days are ever exactly the same. Each spin occurs from a slightly different position in orbit, under a subtly different angle of sunlight. The seasons advance, the stars shift, the calendar moves forward. The Earth doesn't just rotate in place, it drifts through space as it turns. Every dawn happens from a new position in the universe. Every sunset carries you to a slightly different point along the orbit's curve. Time, in its most physical sense, is simply the measure of this movement, the distance the Earth has travelled since the last sunrise. It's strange to think that the sense of constancy we feel is built on motion so vast. The planet's orbit is a highway of unimaginable scale, but it feels local, intimate and familiar. The sun rises, the light warms the air, the days follow one another. The cosmic reality behind that pattern is hidden by the perfection of its continuity. You're moving 30 kilometres every second, yet the air doesn't stir, the ground doesn't tremble, the sky appears calm. The same physics that hides the rotation hides the orbit too. The constancy of motion creates the illusion of stillness. The orbit itself is the result of balance, not between speed and rest, but between gravity and inertia. The Earth is falling toward the Sun all the time, pulled by gravity, but it's moving sideways fast enough that it never falls in. The two forces balance perfectly, the pull of the Sun's mass drawing inward, and the forward momentum of the Earth's motion carrying it around. The result is an endless fall that never reaches the ground, a perpetual curve through space. It's the same principle that keeps the Moon around the Earth. In both cases, motion becomes stability. The orbit is not escape and not capture, but a harmony between the two. That harmony is everywhere in the solar system. The planets each occupy their own balance points, their own speeds and distances. Mercury, closest to the Sun, races around in just 88 days. Neptune, farthest away, takes more than 165 years. The Earth's period, 1 year, is the result of its specific distance and the gravitational pull at that range. The farther from the Sun, the slower the motion required to maintain orbit. The closer, the faster. The solar system is a hierarchy of speeds and balances, each body falling and moving at just the right rate to coexist with the others. In the long history of astronomy, understanding that balance was one of humanity's greatest achievements. For centuries, people saw the heavens as turning around a stationary Earth. The daily rising and setting of the Sun, the monthly motion of the Moon, the yearly cycle of the stars, all of it seemed to circle the world. It wasn't until Copernicus, Kepler, and Newton that the truth became clear. The Earth was not the centre, but another traveller. The apparent motion of the sky was the result of our own motion through it. The rotation and the orbit working together produced the illusion of a cosmos that revolved around us. The reality was simpler and more elegant. We were part of the rotation ourselves, moving through the same laws that governed the stars. Kepler discovered that the orbits were not perfect circles but ellipses, shaped by gravity. Newton later showed that the same force pulling an apple toward the ground kept the planets bound to the sun. That realization unified the heavens and the earth. It meant the same physics that makes a ball fall makes the earth curve endlessly through space. It meant motion was universal. The same balance that keeps your feet on the ground keeps the earth in orbit, and keeps the moon circling the earth, and keeps the planets circling the sun. The orbit isn't something separate from life here. It's the cosmic extension of the same laws that shape everything you can touch. If you think of gravity and inertia as opposites, one pulling in, one pushing forward, the orbit is their compromise. The Earth drifts forever in a path curved by the sun's pull. Without gravity, it would fly off into darkness. Without motion, it would fall inward and be consumed. The balance between those two states creates the endless fall we call orbit, the same fall that defines time itself. Every second you live, the Earth moves a little farther along that curve, carrying you with it. Every year, it returns to almost the same position, though never exactly, because the solar system itself moves through the galaxy, and the galaxy moves through space. The Earth's orbit is both circular and unending, but its path is never the same twice. The planet is always drifting, always in motion through a universe that never stops changing. From the surface, that vast movement feels abstract, but you can see hints of it in the sky. The shifting constellations through the seasons are the visible trace of the Earth's orbit. In winter, you see stars that lie in one direction from the sun. In summer, you see those on the opposite side. Each season reveals a different slice of the galaxy, a different window on the cosmos. Over a year, the orbit turns the entire sky before you, one section at a time. The world's rotation spins that view every night, but the orbit moves it slowly, steadily, across the year. The result is a double rhythm, daily rotation, yearly revolution, the two overlapping like the hands of a clock measuring different intervals of the same flow. The orbit is also a source of stability. Its constancy ensures that the amount of sunlight reaching the Earth remains within a narrow range, neither too much nor too little. If the orbit were more elliptical, the climate would swing between extremes of heat and cold. If the distance to the sun changed too much, the delicate balance that allows liquid water, and therefore life, would fail. The Earth's near-circular orbit, maintained by gravitational interactions with other planets, keeps conditions steady enough for evolution to proceed gradually. The path through space isn't random. It's refined by time, sculpted by balance, sustained by the very motion that might seem invisible. Even the moon's presence affects that balance. Its gravity not only slows the Earth's rotation, but also stabilizes the tilt of its axis, keeping the seasons consistent. The Earth and Moon move together around a shared center of mass, a point that lies about 4,600 kilometers from Earth's center. The pair travels as one through the Sun's gravity, bound by their mutual orbit. If you could trace their path precisely, you'd see the Earth wobbling gently as the Moon tugs at it, like a dancer guiding a partner in slow, measured turns. That small motion, repeated endlessly, adds to the complexity of the Earth's journey, a layered movement of spinning, orbiting, and drifting through space. Beyond the orbit of the Earth lies the vastness of the solar system, each planet following its own curve, each contributing to the collective balance. Jupiter's immense gravity shapes the orbits of countless asteroids. Saturn's moons adjust their parent spin. The entire system is a network of influences, a web of motion so finely tuned that it appears still from a distance. Yet nothing is static. Every orbit changes slowly over time, nudged by the pull of others. The Earth's path, too, shifts in small ways, its shape, its tilt, its orientation, forming the long cycles that influence ice ages and climate over tens of thousands of years. All these movements, spin, orbit, precession, drift, coexist without conflict. The Earth's rotation and orbit fit together like nested circles, each supporting the other. The rotation defines day, the orbit defines year, and together they define the rhythm of life. The sense of permanence you feel when you look at the sun, the confidence that it will rise again tomorrow, is really faith in those motions continuing. And they will. There is nothing in the near or distant future that can stop them. The sun's gravity holds the Earth securely, and the Earth's momentum keeps it moving. The orbit is self-sustaining, an agreement between motion and pull that has lasted for billions of years. Over unimaginable stretches of time, the balance will change, but only slightly. As the sun ages, it will lose mass through the slow release of solar wind, and its gravitational pull will weaken. The planets will drift outward, their orbits expanding. The Earth will move to a slightly higher, slower path. The change will take place so gradually that it will be imperceptible even over the entire span of human civilization. The rotation will slow fractionally. The orbit will widen. The pattern will continue, the system adjusting to maintain its equilibrium. In the farthest reaches of time, when the sun's life ends and it swells into a red giant, the Earth may be consumed or cast away, but until that point its orbit will remain faithful to the same laws. The drift through space will go on, carrying the world through light and shadow, through seasons and centuries, through everything we know and beyond. The rotation will keep the planet turning, and the orbit will keep it falling, gracefully, forever. The Earth is not just spinning or travelling, it's drifting in balance, suspended in a state of motion that feels like stillness. Every second it covers 30 kilometres around the sun. Every minute it completes a little more than 1,000. In the time it takes for you to breathe, the planet has moved farther than any human will ever travel in a lifetime. Yet you feel none of it. You sit within that motion as comfortably as you sit within the atmosphere. The drifting is absolute, but it feels like home. When you look at the sun, you're looking at the centre of that motion, the gravitational anchor that defines the Earth's path. The light reaching you took 8 minutes to cross the space between, arriving on a planet that has moved hundreds of kilometres since it left. You're always seeing the sun as it was a few minutes ago, always living slightly in the past of that light, always moving forward in space as the photons arrive. Even perception carries the trace of motion. The orbit isn't a journey with a destination, it's an endless loop, a repetition that feels eternal because it's balanced. The drifting doesn't lead somewhere, it simply continues. The Earth's motion around the sun is not progress or travel, but continuity, a cycle that renews itself with each completion. It's the physical embodiment of time without haste, movement without end. Every day, every season, every lifetime is part of that drift. You rise, sleep, live and dream while the Earth carries you through space, turning and falling and turning again. The stars shift, the sky changes, the sunlight softens, and the orbit continues, unbroken, unseen. The drifting never stops, and that is what makes the world stable. Motion is what holds everything together. The Earth spins and travels, and you move with it, effortlessly, through the geometry of the cosmos. The orbit is the thread that ties the world to the sun, the rotation the pulse that keeps its rhythm alive. Together they form the quiet machinery of time, a system so vast, so precise, and so constant that it feels like eternity. And as the world continues its drift, as the orbit carries it through light and shadow, the same balance that began when the solar system was born still holds. Gravity, motion, inertia, and light remain in perfect conversation, keeping the planet steady in its endless fall. It's the same motion that began billions of years ago, still unfolding, still smooth, still silent. The Earth turns, the Earth travels, and together, those motions make the only home we've ever known. A world drifting in orbit, eternally moving, forever still.